Okay, let's get started, please. Good morning. Thank you for coming early on this hot day. My name is Bruce Howe. I'll be moderator for this session, Civil Applications, the use of CTBT International Monitoring System data in support of disaster risk mitigation. The basic format will be that we'll start off with a brief introduction for each person with a few PowerPoint slides for each person, addressing their particular area of expertise and connections with CTBT. Then we'll move to panel questions and discussion, and then open up the floor for questions from all of you. If we could have the first slide. There. Okay, good. So just myself, I'm an ocean engineer and physical oceanographer at University of Hawaii. My areas of interest are observing the oceans acoustically, developing sensor network infrastructure, including underwater GPS that could make use of the CTB hydroacoustic data for ocean temperature, and while providing navigation and positioning service, working on smart cable systems to add sensors to telecom cables spanning the oceans. So next will be Elizabeth Blanc. If you could move the slide. Could we have the slide control? There it is. Yeah.
Thank you. Good morning to all of you. I'm Elisabeth Blanc, Research Director at the French Alternative Energy and Atomic Energy Commission in France. And I'm interested by infrasound monitoring for the verification of the CTBT. And I was involved already in the 90s for the definition of the specification of all the IMS system in the infrasound technology. And my main interest now is to establish which are the uncertainties for the from the middle atmosphere variability, which affect infrasound monitoring and the simulation performed for routine processing. And thank you. And we use now infrasound IMS data for application like remote volcanic monitoring for civil aviation. We are able to detect volcano at a distance of several thousands of kilometers, and this is also this method can be used also for meteorite monitoring and weather extreme event. And now I proposed and I coordinate a European research infrastructure project called ARISE. It integrates the infrasound IMS network with LIDAR, radar, and other systems. And the objective is to have a better knowledge of the middle atmosphere dynamics for reducing uncertainties.
You had other slides. Do you want to show those?
Depends if you have a question.
You could run quickly through.
Just now, you prefer?
Yeah.
Okay. And so I prepare several slides to explain our work using infrasound technology. And we interact with CTBT for civil disaster risk mitigation. And I show in this figure some example of work performed for remote volcano monitoring. So we use IMS system which is fantastic for atmospheric studies. It is a unique system for data quality, continuity in observation. It's global coverage, and eruption can be detected very far. And this technique is complementary to other techniques based on satellite observation. And for example, I show in this figure here, there is a comparison between satellite data and infrasound eruption detection. And you see in black the infrasound detection, and we see all the eruption of the volcano, while with the satellite in blue, there are many interruptions because the satellite is not always over the volcano, and I miss a lot of eruption. So this is quite important to use our infrasound data for infrasound monitoring. And we develop this volcano information system using IMS. Eruption can be automatically detected, and the notification and confidence criteria can be sent to VAC, Volcanic Ash Advisory Center, in relation with the CTBT to provide alert for civil aviation in case of eruption of ash in the atmosphere. And we have also close cooperation with WMO, mandated by the International Civil Aviation Organization to coordinate and disseminate information on the volcanic ash cloud. And there is a large interest, of course, in the case when volcanoes are not instrumented.
Okay. We could come back to after we
okay.
So Laura Kong has been director of the International Tsunami Information Center since 2001, and the center supports the UNESCO Intergovernmental Oceanographic Commission in its effort to deploy tsunami warning and mitigation systems on a global scale. The ITC, as it's known, has been primary provider of information expertise for technology transfer, awareness, training, and capacity building in tsunami warning and mitigation for the IOC. She's been with ITIC since 2001 after graduate studies in seismology at MIT and research. Laura, please. Advance. Keep going. Yeah.
Good morning, and thank you for actually inviting me to be part of this panel. So I thought what I'd do is just give you a quick run through of what we mean by tsunami and tsunami warning and mitigation, and I just put this up to kind of bring us all back to 2004, and it was a wake-up call for not only us who've been working on tsunamis since the 1960s, but also the world, where nearly 230,000 people perished over 14 countries. It was really an effort on the part of the UN, working under the guidance of UNESCO and the Intergovernmental Oceanographic Commission, as well as WMO, UNDP, and I just add CTBTO and their contributions starting in 2005 to share the IMS data with all UNESCO-designated tsunami warning centers around the world. But it was really about not only putting in the detection systems, but also making sure that we equip individuals and communities so that DRR, disaster management, and people-centered early warning systems. So there are now 4 regional tsunami warning and mitigation systems, starting in the Pacific in 1965, but then in 2005, the Indian Ocean, the Caribbean, and now the Mediterranean and North Atlantic. So what do we mean about end-to-end early warning? It's really about the detection part, the part in the ocean of detecting the tsunamis, not only the tsunamis, but also the earthquakes, because about 80% of tsunamis are generated by earthquakes, the great earthquakes. We want to detect those. We want to make sure our national tsunami warning centers, our countries are able to assess a threat and issue the warnings, and they're really issuing it to the locals, the communities, and making sure that those communities are prepared. So that's the alert and the signage and a lot of the public awareness and education that must take place. So this is a technical audience, and we put this slide in here just to give us a comparison of where we were prior to 2004 and where we are now and where we want to go with the UN decade for ocean science and sustainability. So where we want to be in 2030. So the first star is where we want to actually detect and warn, perhaps in the first 10 minutes. And what we know is that in order to really drive informed evacuation so our politicians don't come back at us and say, you issued a warning and there was no wave or was not destructive waves, we want to be able to forecast. In order to be able to forecast, we need to characterize the earthquake in real time and very quickly and accurately. And we also need to be able to provide a wave amplitude or forecast in time so that mayors and emergency management can actually say who should evacuate and when they should do that. So in 2004 and before, we were looking at perhaps in the orange line, something like anywhere from 15 to 45 minutes before we could actually get a forecast. With CTBTO and new methods and improved modeling and computation, we're now down to maybe about 15 to 20 minutes, the green line. But where we want to be in 2030 is we want to get within the first 5 to 10 minutes where we can get a forecast. And so down at the bottom, I'll just call your attention to some of the technologies that are coming on board, some of the data that are now being available that we need to develop algorithms so that we can operationalize and make them available, reliable, and accurate in a few minutes. So where is that? It's really about thinking about the oceans. What can we do to put into the oceans that will help us detect a tsunami faster? And if we can detect a tsunami faster, then we can actually make an accurate forecast. So it's a little bit hard to see, but cables, what can we do in terms of these smart cables that are going across the ocean? Can we partner with industry and to put them in 100-kilometer spacing? Can we put these, what we call GPS buoys, so surface buoys that are actually measuring the ocean offshore and actually use that to drive our forecast? So there are a number of different technologies that are coming on board, and right now it's a research to operations effort, but some things we want to be looking forward to in the next 5 to 10 years. So I just want to close and say, well, 80% of our tsunamis are generated by earthquakes, and therefore we have concentrated on earthquakes. There are also, as you know, in the last year, a number of what we call atypical tsunamis, those generated by volcanoes, landslides, an example of which was Palu, which was a strike-slip earthquake, caused quite a bit of damage, liquefaction in Palu in 2018 in Indonesia. In 2017 in Greenland, a subaerial landslide that caused a tsunami. And then finally, last year in December, Krakatau, which was a volcano, which was a landslide that also caused a tsunami. So a lot of things to be considering besides earthquake as we try to mitigate tsunamis and save lives Thank you.
Okay, thanks, Laura. Can you pass the pointer on? Next is Ricardo Mina, professional in risk, crisis, and disaster management. He's been with the UN since 2002 and in the Office of Disaster Risk Reduction since 2009, and now leads the branch supporting and monitoring the Sendai framework implementation. Ricardo?
Thank you very much, Bruce. And actually, let me start by, well, first thanking organizers for having invited the UN Office for Disaster Risk Reduction to participate in this panel. Let me start by talking a little bit about the Sendai framework for disaster risk reduction. This is part of the framework agreements that the international community signed in 2015. As you must know very well, the Sustainable Development Goals, the Agreement on Climate Change signed in Paris. Actually, the Sendai Framework was the first of such agreements signed in the city of Sendai in March of 2015 for an implementation period covering 2015 to 2030. This is the global plan to reduce the impact of disasters. And it has a number of very interesting features which make it different than other frameworks of this kind that were adopted before the SnT framework. I would perhaps name just the predecessor of the SnT framework, which was the Hyogo framework for action that was adopted for the period 2005 to 2015. So the SnT framework brings a number of new elements. First, it's the first such frameworks or agreements that has defined global targets and indicators to be achieved. And in the particular case of this framework for the period 2015 to 2030, there are 7 global targets. First of one, reduce the number of people killed by disasters. Second one, substantially decrease the number of people affected by disasters. Third, reduce the direct economic impact of disasters. Fourth, reduce the damage to critical infrastructure. And then there are 3 that we have to increase. One is increase the number of countries with national and local disaster risk reduction plans. Actually, this is the target that comes to deadline in 2020. So we are putting a lot of emphasis on this target with all of our member states. The other global target relates to the increasing the economic flows for disaster risk reduction by 2030. And last but not least, increase the number of countries that have access to multi-hazard early warning systems and disaster risk information and assessment to people by 2030. Now, the framework has also 4 priority areas which deal with better understanding risk and better understanding risk in all its dimensions, both from the understanding of the hazard itself, but also on the exposure and vulnerability elements. The second priority deals with strengthening disaster risk governance to manage disaster risk. The third, emphasizing again on investing in disaster risk reduction for resilience. And the fourth, on enhancing disaster preparedness for effective response and to build back better after disasters. The goal of the SnT framework is to prevent the creation of new risk, reduce existing risk, and strengthen the resilience of people, particularly in countries that are highly vulnerable and prone to natural hazards. Now, this is a very quick overview of the SnT framework, and you have already, I think, thought in your minds about, okay, what are the entry points for monitoring systems like the one that CTBTO has put in place to support also the implementation of the SnT framework. But before entering into those, I have to also make 2 important notes that make the SnT framework particularly interesting in today's world. One is that it is directly linked with the Sustainable Development Goals. Actually, some of the targets and indicators of the Sustainable Development Goals are interlinked with some of the global targets of the SnT framework, particularly with regards to SDG 1 to reducing poverty, SDG 11 on sustainable and livable cities, and SDG 13 on climate action. That's one. The other one is that by adopting the SnT framework, member states decided that it was time to expand the scope of application of this type of international frameworks, and it decided to not only focus on natural hazards, but also on man-made hazards, as well as the technological, environmental, and nuclear hazards and risks. So going back to my previous questions, what should be the entry points? And there are many. First, of course, and that's why I put on my first slide, target G, substantially increase the availability of and access to multi-hazard early warning systems and disaster risk information and assessment to people by 2030. This is obviously the most, from my perspective, the most evident entry point to try to use all available technologies and all available information to allow countries to meet this global target by 2030. And of course, it's very important to make the effort to link communities, because sometimes we are very much geared towards working just with those that are dealing directly with the subject matter without opening doors and reaching out to other experts and other sectors and other disciplines that may have important contributions to make for whatever your objective may be. In this specific case, the use of new technologies and, for example, such as the one that CTBTO is using currently, could enhance a lot the capabilities of countries to enhance multi-hazard early warning systems. But I don't know to what extent. I think it is only a few countries where the national organization in charge of monitoring and supporting this international monitoring system that CTBTO has put in place are actually in contact with those dealing with the geological hazards and the hydrometeorological hazards and other hazards that could benefit from the information that CTBTO is generating. So this is one entry point. The other entry point is actually the priority area 4, which, as I said, emphasizes on the need to enhance preparedness and also work in a preventive way for all the recovery, rehabilitation, and reconstruction efforts and the Build Back Better principle. There is also, I think, room for a lot of discussion that could take place on ways in which those preparedness efforts can be enhanced through the use of this type of new technologies. And the third one, which I would mention, and then I'll stop, would be related to priority area 1, which deals with increasing the knowledge on actually disaster risk, understanding risk. And risk, as we know, it's a systemic matter that cannot be looked at in a vacuum. We are saying, and I know that I have a modeler to my left, Stephen, we are saying that the time to model individual hazards is over. We cannot look independently at individual hazards because there are many, many systemic connections that can create cascading effects or that can trigger other types of hazards that can have an impact on humankind. So, of course, the understanding of some of the disaster risks that CTBTO is also developing should be put also to contribute to this priority area for better understanding risk and actually achieving the targets of the SnT framework. But I stop here. I know that we have a second round where I can elaborate a bit further on these issues. Thank you.
Good. The next person, Stephen Pawson, is in global modeling and assimilation at the NASA Goddard Space Flight Center and working on atmospheric and Earth system models. He's been chief of that section since 2014, having started there 15 years ago after working at Oxford and the Free University of Berlin and graduate studies in meteorology at the University of Edinburgh. Stephen?
Okay. Yeah. Good morning. Thank you very much. And I'd like to, first of all, thank you for the opportunity to be here and to speak to you from this panel. I'm from the Global Modeling and Assimilation Office at NASA's Goddard Space Flight Center, and I'm going to just try to give an overview of our work. The animation running while I'm speaking is actually a simulation of the atmospheric ash dispersion of a volcano that never happened, and I'll come back to that in a short while to tell you about the capability I think that's pointing to. We run the the Global Earth Observing System model in Goddard, and that is a configurable model. We can run it at extremely high resolution, down to about 3 kilometers globally, if we're interested in atmospheric circulation. We're running it every day at about a 10 to 12 kilometer resolution, producing weather forecasts. And we also use it at a global resolution of around 50 kilometer for reanalyses, and a product of ours that goes out there is MERA-2, which is quite widely used for studies of the atmospheric circulation over many years. Our main reason for doing this is not to compete with the meteorological operational centers in the world, but rather to demonstrate the impacts and value of new data types on these types of products. And so, for instance, MERA-2 is the first global reanalysis that had interactive aerosol contributions in it from NASA satellite observations. And that's the real key, that we're focused on using NASA satellite data to show the impacts and show the relationships of the non-standard, possibly non-physical fields, the chemistry and biology, with the physical structure of the Earth system as well. We have used the CTBT data very little in the past, but one interesting study that we did actually publish a few years ago was during the summer of 2006. There were severe fires in the neighborhood of the Chernobyl region in the Ukraine. And there was some concern about the reactivation of the nuclides there getting back into the atmosphere. So we did actually do a study there of the potential reactivation of radioactive nuclei on aerosols, and transported those. And we used the CTBT as an observations as an evaluation for that study. And the good outcome of that work was that we found there wasn't really a significant health hazard posed by that reactivation, but it was a quantitative study that we did using the CTBT data. There are many other things we could do, and we could go from regions of inverse modeling, trying to understand sources and sinks. But I'll focus on the animation, and I'll actually just try to replay it while it's happening. What we're seeing here is an eruption of Mount Agung in 2017. There was a lot of seismic activity around there at the time, and there was a lot of concern about a severe eruption comparable to its 1963 eruption. So what we did, we set up our system to be able to take that emission and put it into our weather forecast, essentially. So essentially, we emitted an ash cloud from Mount Agung, and this is its dispersion through the atmosphere. And you'll see, it's fairly localized, but it does have a fairly large regional effect after 4 to 5 days. And the concern in this instance would be aviation hazards. But of course, there are many other concerns about volcanoes. For instance, if it's a much deeper eruption getting sulfate into the stratosphere, there are much more long-term effects that can affect the seasonal predictions, and that can affect how we're able to predict droughts and flooding events, for instance, in different countries worldwide. So I could see future uses of, for instance, real-time estimates of where a significant volcano is happening that would help us pinpoint where it's going to be and help us do two things. One of them is looking in NASA's satellite observations to help us isolate plumes that we're seeing. And the second one is to initialize this type of emission in the correct location in the model to be able to provide forecasts such as the one that you're seeing on the screen right now of ash and its distribution around the world. And I think that's where I will stop for now. Thank you. Okay, good. And then last but not least, Juan Carlos Villagrán
leads the UN Office for Space-Based Information for Disaster Management and Emergency Response, SPIDER, in Berlin. After a graduate study at University of Texas in experimental condensed matter physics, he's been at the UN since 2004, starting at the United Nations University for the Environment and Human Security. Juan Carlos.
Thank you very much. I would say that from the side of the space community, there's a parallel complementing effort to CTBTO to facilitate access to space-based data. And I think that we should find ways to cooperate more in facilitating this combination of the two types of data. And of course, when we talk about satellite technologies, well, you should be aware there are 4 of those, let's say. The one that comes to mind every day is Earth observation. We look at Earth from above, and we got a lot of bands to look at, whether it's in the violet, the optical, the infrared, then the far infrared, where we could see through the clouds. Satellite meteorology has been around, contributing to forecast tropical storms. And of course, satellite communications are the backbone to a lot of sensors that are deployed in the field that are used by observatories to make those essential forecasts, to warn people about impending events. And more we see the use of global navigation satellite systems along these lines. One of the typical applications that we see in the area of response efforts is to guide pilots to flying helicopters to landing sites where they need to deliver provisions. And we see more and more these unmanned aerial vehicles making use of these technologies to fly supplies to areas affected. When we look at what are the added value of uses of satellite technologies, one of the things that we have seen is that there is a vast archive of satellite imagery. If you're looking at droughts, for example, there's probably about 40 years of archived imagery every month. If you look at the US and their MODIS sensor, there's 19 years every 8 to 16 days. So you could really answer the question, how severe is the vegetation being affected right now by a drought in comparison to droughts in the last 18 years? And you can do that every 16 days. So you could really answer comparatively how severe the drought is in vegetation right now. In case of those events, hydrometeorological events like floods, in very large basins where it takes days for the floods to proceed, you could see through the clouds with radar imagery and track how that flood is progressing downstream. There's an interesting application we saw in Vietnam last year where they deviate the waters of the Mekong Basin to the rice fields way before it reaches cities. So they're able to minimize floods to cities by diverting the water to the rice fields. And you can see that through satellite imagery, how the waters are being diverted. And of course, when you look at Earth observation, one of the things you do see is the most up-to-date view of what is exposed. If you see a port and you see urban, semi-urban areas, and you need to start thinking about evacuation routes, whether it's for people or for cars, having that most up-to-date view allows you to identify as an early warning manager potential evacuation routes. Equally important is identifying the location of vulnerable groups so that you can improve your warning strategies, knowing who to warn first and so on. So, as I say, there's a complementary part to what CTBTO does with data from the ground, with what the space community is collaborating from the atmosphere, from the outer space part. And we look forward to that synergies with CTBTO.
Okay, thanks. So now I'll ask a question that the panel can respond to. And so for your particular areas of interest here, what are the strengths and weaknesses involved in your areas, and what are the bottlenecks, and how could the system be improved? So if we could just go through just verbally here, one by one, like 1 minute each, that would be good. Elizabeth?
Yes, thank you. And the system is already very efficient, but we could improve it maybe in the infrasound domain in performing additional observation in parallel to infrasound technology, because as infrasound propagate in the stratosphere and in the mesosphere, we miss data about the condition of propagation which impact on the detected signal. And so we develop now some synergy with other technology like LIDAR to have a full representation of the atmosphere, and this improves a lot all the detectability and all the accuracy of the results that we can observe. This is an example. And also it's interesting to work on all the full frequency range which is observed by the infrasound sensor, and not only at high frequency, because in the lower frequency part we have a lot of information about the atmospheric disturbances, and these disturbances affect the infrasound propagation, and if we improve the knowledge of this disturbance, we can also improve our capacity in infrasound detection capability.
Laura?
Thank you. So I think the first thing I'd just like to say is to thank CTBTO for actually, it was in January of 2005, which is about 3 weeks after the 2004 tsunami in the Kobe meeting for the World Conference, that it was actually Lucina Zerbo and Sergio Barrientos, who were the head of the IDC, that actually came to myself and Charles McCurry, who's the director of the Pacific Tsunami Warning Center. And they came in actually with the intent of wanting to open up the CTBT data stream for humanitarian uses. So thanks to that for actually putting us on a way forward for all of us to share data. So really the strength is the IMS is a high quality, real-time, near zero latency network that's always going to be available. It's something that countries can depend on, and that's in contrast to often when we look at other types of telecommunications, some of it is by internet, and so we don't have as much as data availability. So I think that would be the strength in terms of another aspect of the CTBT is actually there's a capacity building and training program that is actually helping the NDC staff to increase their capabilities to use the IMS data. And I would just say that in many developing countries where the staffs are very small, those are the same staffs who are also responsible for other types of warnings, whether it's for tsunami or weather. So that's a strength of the contributions of CTBT. I think I'll leave that there.
Okay. Ricardo?
Thank you. From the disaster risk reduction perspective, I think that, and I already alluded to this when I first took the floor, is to find out how we can advocate and actually manage to get communities of practice together. The SnT framework, with its 7 global targets and a list of 38 indicators, has actually an online monitoring system that governments need to use and report back on implementation on a regular basis. For target G, which we discussed about the increased access to multi-hazard early warning systems and risk information, there are a total of 6 indicators, and they have to do with things like, having actually the multi-hazard forecasting systems in place, the coverage of early warning information, the number of local governments that have plans to act on early warning, the availability of risk information and assessment, and the population that's protected through preemptive evacuations. Now, to support countries achieve these indicators of target G, what I think would be fundamental is to make sure that the national SnT framework focal points, which are officially designated by member states, are actually in close contact with the national entities that are supporting CTBTO, so that the information that is produced by both communities can be put to service for this achievement of this goal. And this is not an easy task, because just to use an analogy, we have been for a long time trying to connect with the communities that are dealing with climate change. Because from the adaptation side of climate change, there are lots of things in common with the disaster risk reduction community. Most of the issues related to adaptation refer to how to adapt to a changing climate, which means also either increased or decreased precipitations or increased intensity of some of the hazards as they manifest themselves, and also with more frequency. So they are intimately related. And although it would make absolute sense to have those two communities working together, for example, member states have to prepare national adaptation plans on climate change. And they have to also develop, by 2020, as I said, national disaster risk reduction plans and strategies. But putting the two communities together is not an easy task. I suspect that the same would be the case for putting together SnT framework focal points with CTBTO focal points at the country level. Because also, in the case of particularly CTBTO, the national entity in charge of following up on their commitments and the agreements that they have signed to is not a, let's say, single type of entity which is responsible for this. I was just having a discussion with CTBT colleagues, and in some cases it's a scientific and technical organizations, in other cases it's probably an academic center, in others it's actually the Ministry of Defense, and so on and so forth. But for purpose of monitoring the SnT framework implementation, actually member states have to reach out to all those national stakeholders that in one way or another can contribute with information, data, or practices around disaster risk reduction. And that would be the best way to also try to promote this information so that these two communities can work together, both in developing the national disaster risk reduction strategies to better understanding risk and to better achieving target G of the SnT framework.
Thank you. Next.
Okay.
Steve?
Yeah, thank you. So looking at strengths and weaknesses and bottlenecks and improvements, I'm going to bring up a couple of examples. The first one is fairly general in terms of the modeling and data assimilation work that we do. And that's really the great advances in technology that have been made over recent years, and the ability of our scientists to take advantage of those. Essentially, we're really dependent on a strong high-performance computing environment, and that gives us the ability to do really forefront scientific experimentation using new data types and many kinds. And I think that a way that this could impact working with CTBT data is essentially the data flows are all in place. There is tremendous ability these days in the world to obtain data from different sources very rapidly and to bring them all together in very complex systems and look at impacts. And so I can see that the scientific potential is there for my group and other similar groups to exploit these observations in ways that we have not yet done. And I'm just very glad for the opportunity to be here to learn about this and do that. The bottleneck I would see potentially there is while we can often readily do things in a research framework, it is often hard to transfer that into a more operational framework, and that is something that we'll have to work on with probably more with operational centers that can do that and take advantage of the capability. And then the second point I wanted to make really alludes to modeling and inversion studies. And I saw this week there's some really wonderful studies using transport and moving to inversions. And I think that this is a really great new opportunity for us to bring the work that's being done with, say, the radionuclide data, the radioactive pollution, into alignment with studies that are ongoing with carbon gases, greenhouse gases, CO2 and other things, and air pollution, trying to understand sources and sinks of all pollutants simultaneously will actually benefit all fields. And I think I would want to encourage everyone to really get together in a much more interdisciplinary way to make sure that the advances made in one part of this are carried over and taken advantage of by other communities. Thank you.
Good, thanks. Juan Carlos?
From the point of view of strengths, I would have to probably remind, since I have a little bit white hair, I remember when satellite imagery came in reels were about this diameter. So you can imagine it was difficult to exchange that easily. So right now we have the internet and you can transmit satellite imagery and download it over the internet. More and more the space community is establishing open data policies that facilitate our access to that satellite imagery. Of course, there's commercial and open software, and one thing that we have from the satellite view is this global view. We can really see what's happening at the global level and compare things in one continent with things in another continent. When it comes to weaknesses, I would say that mostly in developing countries, a lack of awareness. There is this view that the only useful satellite imagery is the one taken a few minutes ago, very high resolution, like a beautiful color picture from 400 kilometers above. So we have to raise awareness that it's a lot more than that. Also in developing countries, we face the challenges and weaknesses of lack of skills in professionals working in disaster management agencies, so we have to develop those skills. On the bottlenecks, I would say, yes, we want higher resolution satellite imagery. We want more frequent. So this becomes big data. If you think that a Sentinel image is about 5 gigabytes, here in Europe, they fly over every 2 days. So if you start multiplying that 5 gigabytes by 2 days in a year, you quickly come to the hundreds of terabytes. And if you see now there's 6 satellites of those, then it becomes quickly petabytes. So the issue is how to start archiving all of this data so that you can, again, reuse it in the combination of archived and up-to-date imagery. So this is one of the bottlenecks, but I'm sure that the IT community will eventually help us solve that issue.
Okay, thanks. I think we're getting to the point we would like to entertain questions from the audience. Could you raise the lights a little? And so if you have a question for the panel, raise your hand and we'll stand up and a mic will be brought to you. In just while I can't see anything, so in the meantime, while someone stands up, maybe I could just ask Ricardo just to maybe re-emphasize perhaps, how directly could CTBTO and the SnT framework work together in a concise summary, because I think that's a very important point.
Thank you. Yeah, as I said, UNDRR, our organization, would be ready to collaborate with CTBTO to make sure that we bring the two communities together. We just had our global platform for disaster risk reduction last month in Geneva. I don't know how many of the national parties that are part of CTBT were actually participating in our global gathering. I would perhaps say that potentially very few. And of course, this is something that we can, through our regional offices and through our global advocacy campaigns and efforts, we can try to bring the two communities together, because I think that they can, of course, mutually take advantage of the knowledge and understanding of risks that they can combined have. So this is, I think, a very practical recommendation, and this is something that, as I said, we would be pleased to support in.
Okay, thank you. Question, audience.
Hello. Dr. James Palmer from Atomic Weapons Establishment in the UK. Possibly a question for each of the panel members. The CTBT IMS data covers many different data types. Single data can be applied to many different problems. So do the panelists have a top one or two types of natural disaster or effect that they would like to see the data specifically applied to? Because that might help the community to focus in on their particular areas of expertise and apply them.
Okay. Yes, one cross.
Bruce, I would say, and to the gentleman, great question, the big killers when it comes to disasters are still earthquakes, landslides, and tsunamis, and CTBTO data has a link to that. And I think it's important that we raise awareness and facilitate the use of that data in these three types of phenomena. As I say, at the end of the day, we're also trying to reduce mortality, and the highest mortality comes from those geological hazards. But it's interesting to see in climate change these global circulation models as well.
Laura?
Actually, in a roundabout way, what I'd like to say is I think a number of us have indicated how we're using different aspects of this IMS data for specific hazards, but I'd like to also turn around and echo what Stephen said, is we're really looking at how we can use all different types of data to look at a specific hazard, to be able to integrate that into a risk assessment that's really going to be useful for people. So in the respect of tsunamis and how Elizabeth has said something about volcanoes and eruptions and how that data can be used to help tsunami warnings. So I think we also want to make sure we look at it in an integrated fashion.
Okay, other? Anyone else?
Want to?
Yeah, I can. Steve?
Yeah, so I think, again, I would support the point about volcanoes as being a significant thing that this may help us isolate and be able to start doing predictions of. Again, any unusual nuclear activity could be incorporated into models in terms of producing a forecast of potential outflow from that in the atmosphere and potentially the ocean as well. But I think as much as disasters and single events are, kind of critical to the environment, I don't think we should neglect the value and importance of monitoring and keep having that constant stream of observations coming in so that we can be constantly monitoring backgrounds. Evaluating the long-term states of our transport models and things is always a very, very valuable aspect of our science, and that I think is one of the unique attributes of the CTBT observations.
Okay, Ricardo?
Yes, from UNDRR's perspective, thanks for the question. Actually, we have recently launched at our global platform a new initiative that's the Global Risk Assessment Framework. And what we are trying to provide through this collaborative effort is a go-to place where the risk assessment community can find resources that may be needed to run models to better understand risk. So in that sense, all the data sets that are referred to the hazards themselves or to exposure and also vulnerability layers could be of great interest. As I said, we are approaching risk assessment from a systemic perspective, and we are fully aware that there is connection between different hazards, and risk now in a globalized planet is actually something that you cannot analyze on from a single hazard perspective. So in that sense, what the Global Risk Assessment Framework is trying to do is to first do a map and gapping analysis to identify where are the areas where the risk assessment community and the modeling community does not have the data, and of course applying principles of open access, open data, and other basic principles for data sharing, etc., that could enhance the possibility of the modeling community and the risk assessment community to better model systemic risk. So we are actually trying to enhance and expand the participation of experts in the Global Risk Assessment Framework. We currently have an expert group that was established based on self-nominations, and we are going to be doing calls for expression of interest for participation in some of the working groups that are being established under this initiative. But I will be pleased to talk with you bilaterally on that. Thank you.
Okay, thanks. I think there's one more question, but very, very quickly, please.
Okay, thank you. Good morning, everyone. My name is Matty Goldberg. I'm from UN Climate Change in the Adaptation program. And I think my maybe one observation at the beginning, it seems to me that the key word for a lot of the conversations that we've had today and yesterday is kind of the aspiration for integration. And I think to me the key challenge seems to be in each case that we have various systems that are developed independently based on certain guidelines that can be very specific, and now the challenge is kind of integrated. So moving to climate change adaptation, and I think this is a question mainly for Mr. Mena. Thank you very much for highlighting those connections there. When I think about the national adaptation plans, how the process has sort of evolved is that there's high-level guidance from the Conference of the Parties that define very general guidelines, and then a UNFCCC institution called the LEG, least developed countries expert group, developed technical guidelines that then governments used on the ground. And my hunch is that there's probably been something similar happening in terms of the Sendai framework. And I think at the conceptual level and in terms of some of the reporting aspects, there's been quite a lot of conversations about integration. I'm wondering about the level of practice. When governments apply these different guidelines, that seems to be the area where most of the integration would need to happen. So it would be great to hear your thoughts about how integration at that level can be strengthened. Do we need some sort of toolbox, or that's kind of seems to be the gray area for me. Thank you.
Okay, maybe.
Thank you very much for the question, and I'm very pleased to tell you that actually the toolbox has been developed. We have been working very closely with UNFCCC and the LEG group of experts to incorporate let's say an annex to the guideline for the development of national adaptation plans on how to articulate that work with disaster risk reduction aspects. Not a long time ago, I think 2 months ago, we had a meeting of the LEG expert group in the Pacific, and actually Kiribati was one of the countries where this tool was piloted. So we are hoping that the LEG is going to be the body that endorses these guidelines to make sure that there is coherence between the two frameworks. And this is something that we are also looking forward to enhancing and upscaling this type of work with UNFCCC. Thank you.
Okay, thank you very much. Thank you, audience, for questions, and let's thank panelists for their sharing their expertise with us. Thank you.
You do atmospheric modeling for the ash cloud dispersion?
Yeah. For me, the first one is this one. I know.
Jetzt? Ja.
So I guess I would be
You will sit, if you stand here, you will have the screen here, in any case. Yeah? Yeah. So, that will do? Okay.
Where do you flick the slides?
We have the
okay,
click over
this
here.
is the most important.
So, they will do it from the lectern. So we go one by one. We go one by one.
So we You're going to stand?
He said you can switch if you want to sit.
No, you don't take one for the team. We're going to do it. We're going to do it from here. Because you're going to do it, and then I'm going to do it, and then everyone else has to.
Exactly.
Yes, and that's a laser.
Hello, hello? So I would. So they said that if you start talking, then the microphone will start functioning. Oh, okay. Okay. So shall we start?
We can share this.
Yeah, I don't mind.
So let's start this. Good morning, everyone. Welcome to this vDEC briefings on experience in using CTBT IMS data for scientific applications. As you know, today CTBTO data are not only being used to detect nuclear explosions, but also to investigate the impact of climate change or to track radiation on a global scale. Access to IMS data for scientific use is possible via vDEC. The Virtual Data Exploitation Center provides scientists and researchers from many different disciplines and from around the globe with access to IMS data to conduct research and to publish new findings. Since 2011, in total 114 contracts have been signed by researchers representing 26 countries. Our panelists today will share their experience in using CTBT IMS data for scientific applications. I would like to thank our panelists for accepting the invitation and to introduce them quickly to the audience. Our panelists are from the left, Professor Tracy Rogers. She is a professor in ecology at the University of New South Wales in Sydney. Her research group studies how mammals overcome the challenges of living within changing environments across evolutionary and contemporary timescales. Tracy's group uses the CTBTO hydroacoustic data to study how whale populations are influenced by changes in the marine environment. Our second panelist from the left, Dr. Dirk Metz, since August 2018 has been a postdoctoral fellow with the Japan Agency for Marine Earth Science and Technology, based in Yokohama, Japan. He did his PhD thesis at the University of Oxford. His PhD thesis was centered around IMS hydrophone data and was titled Remotely Detecting Submarine Volcanic Activity and Monowai Insights from International Monitoring Systems, Hydroacoustic Data. Our panelist, Rodrigo de Negri, is an NDC principal user from Chile who is currently doing a PhD in the Department of Earth Science, University of California, Santa Barbara. He is coordinating efforts between the Chilean NDC Geophysics Department of University of Chile and his research group to improve the monitoring capabilities of volcanic eruptions in Chile with the regional IMS infrasound stations. Professor So-Gu Kim is a director of Korea Seismological Institute and former professor of physics and geophysics at Hanai University. He was an invited professor at Beijing University, China, Institute of Seismology and Volcanology, Hokkaido University, Japan, and University of New England, Australia.
and German Research Center, Potsdam, Germany. The next panelist is Professor Von Jung Kim. He is an observational seismologist working on mostly regional seismic data, viewed to about 1,500 kilometers, and studying earthquakes in stable continental regions. He is currently a research professor at Lamont Doherty Earth Observatory of Columbia University. Together with Dr. Paul Richards, has been working on CTBT since early 1990s. Our panelist, Professor Volvango Plastino, is a professor of applied physics at the Roma Tre University. He is a scientific secretary of the International Security and Arms Control Working Group at the Accademia Nazionale dei Lincei, the oldest academy in the world. He is a member of the Standing Advisory Group of Technical Assistance and Cooperation at the International Atomic Energy Agency. With this, I would like to invite our first panelist, Professor Tracy Rogers, to share with us her experience in using vDEC data.
Hello. Thank you, Yolanda. Sorry, just waiting for the slides. So, as Yolanda described, my group, we're ecologists. So we use the CTBTO data, the hydroacoustic data, to work primarily on whales. And here I'm going to talk about the program we've been doing on blue whales. Now, as ecologists, what we want is really long-term data sets, which is actually really hard to find in the marine environment, going back through time. And the people who've been working on this with me are Gary Trong and Emmanuel Leroy. Now, what we want to do is find long-term signals, particularly to look at climatic changes. So the marine system changes all the time, it's stochastic, so you need to have signals that are longer than those changes within the environment. And that's where the CTBTO hydroacoustic data has been absolutely perfect. Now, blue whales are not only the largest animals that have ever lived, they also have very, very stereotyped calls. And different populations make individually distinctive calls, so we can actually tell different populations apart from their calls. So it's poetic that the same system that's out there recording to monitor nuclear bombs is in the same range that we can find these blue whales and distinguish between these different populations. So I was saying that the different populations have different signals. The ZE ones, these ones here, are Antarctic blue whales. So I'm going to talk about them to start with. So the Antarctic blue whales' calls are beautifully in the same range that the hydroacoustic data is collecting. So the system in place all across the southern hemisphere is also ideally located for us to follow the patterns of Antarctic blue whales across the southern hemisphere. So there are 5 buoy arrays. This one here, number 4 at Crozet Island, has worked on and off, but the other 4 are beautifully monitoring all the oceans of the southern hemisphere. And the Antarctic blue whales feed down here during the austral summer, and then they migrate north to breed. So we are able to intersect them, and they call the whole time, all through the year. So we can intersect them as they migrate past the coast at these temperate locations, as well as when they're heading north to their breeding locations. Now, as ecologists, what we want to do is look at long-term signals. So we match the occurrence patterns of when the whales are with environmental data. And the ocean basins of the southern hemisphere are there are large cycles. Within the Pacific, you have the ENSO cycle, Within the Indian Ocean, you have the Indian Ocean Dipole and the Antarctica Difference System. So these systems are driving changes, interyearly changes that influence the marine environment. So in order to actually understand what's happening with climate change, we need long-term signals that are longer than, say, in the Pacific, the ENSO cycle. It's about a 4 or 5 year cycle. So we need data that is much longer than that. Oops. And what we've been doing is collecting information on from the CTBTO hydroacoustic data on the whale presence, and then looking at other environmental drivers, sea surface temperature, the food, chlorophyll A, krill availability, salps, and sea ice, to look at what drives different patterns with whale migrations. Now these are those Z calls, the Antarctic blue whale calls. And this is the value of that long-term data set. Continuously from 2002 to 2017, there's a record of the number of blue whales that are detected at the bottom of Australia down here at Cape Lewin. Here off South America, here at Ascension Island, this point up here, number 2, and here up in the Indian Ocean. So you can see we're able to get a nice long-term continuous data is collected in the same way. Ecologists, we hate it when data is collected in different ways at different times because you have observer bias. This data is beautifully collected exactly the same way at these different sites through time. So it's allowed us to actually notice this pattern that in some years you have lots of whale detections and other years you have very low whale detections. So we're interested in knowing what is actually driving that. And why we're interested in knowing what is driving that is because the oceans of the southern hemisphere are warming, and the temperate zones are becoming much more tropical, the warming patterns moving further south. So understanding, having a signal to be able to pull apart what's a natural variation from what we're seeing with climate change is what we're actually looking for. And what we've found is that across the southern hemisphere, Antarctic blue whales, the numbers are high when you have in the ENSO cycle in the Pacific. When it moves into the La Nina phase, you have large numbers of whales detected in northern waters, and when it's in the El Nino cycle, you have low numbers of whales detected. Now these are Antarctic whales. They're actually feeding in the Antarctic, and this signal is all the way across the southern hemisphere. So what's happening in the Pacific is a really important driver of what's happening also in the Antarctic. Now I started by saying that different whale populations have different acoustic signatures, and this is just within the Indian Ocean. Each one of the different coloured bands, minus that whale we just looked at, is a different acoustic population of whale. Again, ecologists, what we want is not just a sample size of one population. Here, just in this one site, where we have a buoy, a CTBTO hydroacoustic buoy here and here, we can actually look at patterns in these other different acoustic populations of blue whales. So why blue whales? Who cares about blue whales? Well, the blue whales are actually not only the largest animals in the world, but they feed on one of the smallest animals, these krill, very small krill. And in order to survive, they actually need to have enormous amounts of krill. As they feed, they open their mouth underwater. It's like a parachute, opening a parachute underwater. So it slows them down. It actually literally costs them to feed. So they'll swim past areas of low densities of food. So these guys are actually like a really good signal of what's happening in the marine environment. And that's why the access to this CTBTO data has been fabulous. It's poetic that data finding bombs is allowing us to look at this long-term marine signal. So thanks.
Thank you very much. Now we would like to invite the next panelist. As you will see, hydroacoustic data can be used not only to study whale populations, but also to study submarine volcanic activity. So, Dick.
Cool.
thank you very much for the invitation to be here. Cool. So it turns out that volcanoes are kind of hard to research already when you try to do that on land, and it's even harder to do it when they're in the ocean, because we tend not to know exactly where they are, and the few ones that we have a good location fix on is we don't really know when they go off, because most of them are in very remote places, and due to the submerged nature of the volcanic activity, we can't really tell when they go off. However, using CTBTO data has really sort of helped to improve our understanding of submarine volcanoes in terms of the frequency of their eruptions. And I'm gonna talk about one specific sort of hands-on example of what we have done. And the example will be the eruption of Ahi volcano in the northern Mariana Arc in 2014. So the volcano is located along the Mariana Trench. It's just south of a very small uninhabited island called Farallon de Payajos. And the volcano is fully submerged, as you can see in subfigure B. And in 2014, we detected a high incidence of hydroacoustic signals from that particular location by the CTBTO hydrophone station at Wake Island, which is almost 2,300 kilometers away from the site of volcanic activity. And so if we take a close look at what has happened during that time, is then in the top subfigure you see a spectrogram of the first 8 hours of that eruption. And you can see that there is some very strong signals at the beginning from about 21 UTC on the 23rd of April in 2014, which is probably the breaching of the magma chamber. And then the conduits slowly fill up. And then about half an hour past midnight on the 24th, then there's a real big onset of activity, and we detect loads of arrivals at Wake Island. And in the following subfigure, you can see how then the number of arrivals and their direction stabilizes over a period of almost 2 weeks. And the number of arrivals over those 2 weeks is more than 8,000. So approximately every second minute there is a hydroacoustic arrival at the station from the volcano, which is an important thing to know, because you can see how the background noise during that time it really increases. And for CTBTO, this is something important to know, because of course during that time it would be much harder to detect treaty-relevant events at that particular station. And from a volcanological point of view, what is interesting about these signals is that their frequency content appears to change over time. So you can see in the bottom subfigures that the relative share of the yellow arrivals, which is sort of peak frequency in the 4 to 8 hertz range, really decreases over time. And that is probably related to the cessation of fluid movement inside the volcano. So even though we're really far away from that thing, we can really tell from the IMS hydrophone data something about what might be going on inside the edifice. And actually the acoustic resolution of the hydrophone array is much better than the seismic resolution of the broadband stations of the IMS network for this particular location. So if you look at the left figure here, you can see that sort of the magnitude of completeness, that is where the curve drops off of the bin detections, is about 98 decibels, and you don't need to worry about that particular number. But you can see on the right-hand side that if we compare this to the seismic magnitude of events that have been detected in the same location using IMS stations. This is about 1 order of magnitude lower than the lowest seismic, the lowest magnitude of any seismic event that the IMS has ever picked up in the same location. So there's really some sort of, so broadly speaking, some sort of superior sensitivity of the hydroacoustic data over the seismic data in this location. So in conclusion, the IMS data plays a vital role in identifying the location and timing of submarine volcanoes, and it also helps us to understand better what might be going on at the sites where there is eruptive activity in the ocean. Thank you very much.
Thank you very much. We will ask now Dr. Rodrigo De Negri. As you will see, volcanic activity can be studied as well using infrasound data.
Good morning, everyone. Thank you, Yolanta, for organizing this panel. It's a truly privilege for me to be here presenting my research work, which after a couple of days is in SnT 2019. I can fairly say that it's just one of many. I will try to summarize it and highlight the role of vDEC as the source of data I've been using. In short, I'm trying to improve the detection and source location of possible volcanic eruptions in South America using IMS stations. To do so, I'm using historical data from vDEC to test our ideas with the aim of a real-time implementation for IMS stations. I'm from Chile, a country that is placed along the boundaries of the subduction of Nazca Plate below South American Plate. Because of this, I felt several strong earthquakes in my life. I've seen the effects of a big tsunami and especially the consequences of big eruptions like these 3 listed here. Chaitén in 2008, Puyehue Cordón-Cauye in 2011, and Calbuco in 2015. These 3 eruptions generated huge ash plumes that moved mainly to the east due to tropospheric winds present in winter. This affected directly large extensions in the south of Argentina, but also several countries in the continent. Here we can see some photos of what happened after Puyehue Cordón-Cauye erupted in June 4, 2011. I'm especially interested in detecting, locating, and characterizing this kind of eruptions because the hazard that they pose for the local population and civil aviation in South America. So first, let me introduce the usefulness of infrasound. Infrasound is basically acoustic waves, just like the sound coming from my voice now, but at a frequency that is below audible. You can't hear it. It's below 20 hertz. This kind of sound is produced by plenty of phenomena, not only volcanoes, in the earth like meteoroids, the ocean waves, and of course human-made phenomena like explosions. Infrasound has a great property because it's low frequency, it can travel really long distances with relatively low attenuation, being detectable all around the globe. And as I said, volcanoes are a particular kind of source capable of producing these signals. Whenever you have an interaction between the surface and the atmosphere, like an open vent volcano that produces an ash cloud like the figure in the top left, there will be a clear time-punctuated source that we can observe using infrasound. Here is where IMS network becomes a great tool to globally listen for these kind of sources. So vDEC enables us to use historical data to test and understand these kind of eruptions from an infrasound perspective. In the panel on the right, you can see, for example, the waveforms detected in I-41 in Paraguay. That's about 2,000 kilometers from Puyehue Cordón-Cauye. And even in this raw waveform, you can still see the onset of the eruption and several other phases. So here's where vDEC gets essential for me, at least, and for my research group. We want to assess how well our location method works under high seasonal winds, like the ones we have at southern latitudes, like in my country. So we will define a maximum range, about 5,000 kilometers from each one of these 3 volcanoes, This is a table that shows an example for Puyevo-Gordon-Cauye. There are 7 stations around following this criterion. And we define a time window of 21 days around the start of the eruption. And we considered, well, all the possible stations, as I said. From this raw waveform data, we will make use of array processing techniques in each station to try to locate the eruption with a cross-variance approach. That is, using the apparent azimuth from where the signals come from for each one of these stations and try to find the source using that idea. So without this valuable data, we wouldn't be able to understand the real effect of seasonal winds that I'm going to show you. But first, let me explain a little about what I'm doing here. This is a scheme, it's a general idea of how are we integrating several tools in order to find a corrector source, like as we call it. It has 2 main parts. The top of the scheme has several white boxes. It's like that's modeling the expected of we're trying to model the expected effect of the atmosphere winds on physical properties in height over the ray paths. And that is to find what is the expected azimuth deviation. And in the bottom part, you see these green boxes. That means half of our project is based on real data that we obtain from vDEC, and we process that with PMCC. So we take the detections and correct this azimuth deviation, and then we apply IMS vDEC, that is basically a cross-variant approach to find the corrected source. So here you can see, for example, our results for Puyevo-Gordon-Cauye without and with azimuth correction. In the left part, you see, well, we predicted long winds towards the east. I guess there's an arrow that is missing there. But in this time of the year is winter. We predict strong winds to the east. And you can see from the data, if you don't apply azimuth correction, the apparent source has a huge misfit of 226 kilometers. There is a red triangle there in the zoom in the left part, and a circle that is red that shows where we think is the apparent source following this idea. Now, once we estimate the azimuth deviation, we can apply this correction to our data to find that now the source is 75 kilometers from true, which is a great improvement, and this could be effective then to constrain the area where we need to raise an alarm or maybe to launch more in-detail monitoring with other complementary methods. It's important to mention that thanks to this statistical approach, this is a prediction that could be ahead of time and stored in what we call lookup tables for each station. And of course, this is a prototype that we want to improve in short term, using real test cases with vDEC data detections. So let me conclude this considering the importance of IMS data, access for research purposes through vDEC. I think this is and will be, without a doubt, a boost for infrasound, but I'm sure also for hydroacoustic and radionuclide research. We have a multi-year database from IMS that gives us a window to understand big-scale temporal and spatial phenomena in Earth, which is becoming more and more important these times. That's also really a crucial point. And in my research, vDEC is a fundamental tool. I mean, it's a fundamental source of information. I hope in a non-far future, this will allow us to improve global monitoring of energetic infrasound sources and big eruptions. I guess that was the thank you slide.
Thank you very much. So now we will move to seismic data.
Good morning. Thank you for the invitation. I'd like to talk about source depth and okay. Okay, now thank you very much for invitation today I would like to talk about the source depth and the characteristics of DPRK nuclear tests 2006 up to 2017 using regional and teleseismic data. North Korea conducted 6 nuclear explosions, and we estimate the source depth around 2,000 meters, which is very unusual compared to other scientists. I mean, the most relative method. Our determination is absolute method, which is based on the teleseismic PUA arrivals and also including the real wave amplitude spectra as well. Today, I want to show something unusual. I mean, there are velocity anomalies and some depth phase delay time anomalies, depending on the seismic arrays. So here we see some of them, like ARCS, which is located in Scandinavia somewhere, and especially ASAR, Alice Springs in Australia. They already show up the spectrum at the low frequency, which indicate that they may be related to the low velocity structure. I think it's a kind of a late Paleozoic, the orogeny, Alice Springs somewhere, which makes the PUA arrival delayed. So it makes the depth phase delay times also is delayed. And other stations like an NVAR, PDAR, which are located in a high elevation, about 2,000 meters. Also, there's some wind noise, which makes we can see the spectral noise is hard to determine because of some wind noise. And I'll show also some other stations. I will also move a bit fast to this one. Just a minute. This one. This is a Finesse in Finland, Scandinavia. And the spectral nodes are always at high frequency, which means they may be related to the high velocity PUA, high velocity upper crust in the Scandinavian shield. And we move back forward. Also, I want to show even the near field like KSRS and the USRK. KSRS in Korea, in the Korean Peninsula, which is very good station, seismic array. And compared to USRK in Russia, I mean the Siberia is far east. And the spectral nodes move to low frequency because of the subduction zones. Because they are near the USRK, there is a subduction zone which makes low velocity somewhere, and then which also the KSRS is about 1.75 hertz, but the USRK is more than 1.5, something like that, less than that. That means the PUA velocity must be slower. And also I show this one, the left side, there's some special phenomena, like the 2017 is very high, I mean the big nuclear explosion, which makes magnitude about 6.3. And I say the seismic yield about between 500 to 800 kilotons, something like that. It must be a thermonuclear explosion. And so after the main event, we can see the second event, which is non-tectonic event, after I think the 8 minutes 30 seconds. And besides, we can see the slid down phase. As you see, you can see the right after, immediately after the sub-PP, sub-SP, we see the spectral rules, which indicate there's a slip down phase. I mean, because of this big nuclear explosion, and makes some kind of a spore at certain depths. There must be a spore, something like that. The thing is, most of the researchers are estimate source depth around less than between the 300 to 750 meters, which is based on the relative method, and also is as a master event 2006, which is the first event. And then what they calculate is the elevation difference between the source location and the tunnel entrance, based on, using the satellite image. But we are not sure whether or not the source location is at the same level as the tunnel entrance. And also, we are not sure if the source location is correct, because there's various researchers have estimated source location are different. For example, USGS is different from IDC. That's still we are not quite sure where the source location are. So I say the source depth, our estimate is about at the depth about 2,000 meters near the Mantap, which is very, unusual. This overestimate depths may be affect magnitude as well as seismic yield. So my question is still, there's some problems. What is the seismic yield really? And this is still, I have a question. Thank you.
Thank you very much. Our next panelist, Professor Von Young Kim, is also using seismic data. Please tell us.
This is a pointer here. Good morning. I'm going to talk about research work we do at Columbia University with my colleagues, Professor Paul Richard, David Sharp, and Joran Ekström and Lynn Seitz, and graduate students in the past some 2 decades at least after the CTBT treaty done. So today I'm going to show you a couple of examples of what usually we analyze. There are many cases, but basically small event detections, locations, and identification, and we assign magnitude and estimate yield. These are key areas, of course, the CTBT. And depending upon the data set we use, we can describe as teleseismic or regional. Obviously, regional, the 2017 North Korean nuclear test, latest one, provide both case of large nuclear test followed by many small seismic events. So that will be a good examples. So I'll show you a couple of examples. And these examples, of course, cannot be well studied without IMS data and vDEC support. So we enjoyed those supports. So first one I will show you is teleseismic body wave magnitude. And next one is small event detections. And if there's a time, I can show you about the event identification, but I'm afraid we don't have much time. So let's go to the next one, please. Okay. So here I'm showing you the topic number one. The problem is teleseismic body wave magnitude, which is very traditional and easy to determine. But we have the problem that the latest nuclear test at North Korea was reported with MB, the teleseismic body wave magnitude 5.7 through 6.3, which is quite large scatter. And conventionally we could expect 0.1 to 0.2 plus minus units, but it's large. So we set out to see how this came out. And the data used is IMS data from about 350 stations. These are basically primary arrays, and many of those arrays we count also the each station. Then also, of course, there are thousands of stations now available, at least 1,000 stations we use in global, national, and regional seismic network data. Best of these, of course, very classical P-wave amplitude measurement and determining the magnitude. So here I'm showing you on the right-hand side the map of the IMS array stations, about 50 plus, and the circles and triangles, usually the red circles are the ones, stations or arrays, which shows excess of magnitude beyond average network magnitude. The blue circle shows smaller magnitude estimate lower than the average network magnitude. You can see that the Western European stations and Australia shows very large magnitude values. So residuals about up to 0.5, in some cases much larger. On the other hand, stations in Central Asia and part of North America, you can see blue circles. These indicate that these stations produce magnitude slightly lower than the network average. So each station will have also site response, site effect. But we find that broad regional scale magnitude bias due to probably upper mantle pass, because the group of stations in a regional scale are consistent. So these paths from the North Korea to these IMS stations are something new that we have not been able to see in the past since 1960s. And so these are new area of study we have been carrying out. The next topic is the weak event detection and relative location. Following this 2017 nuclear test in North Korea, there were about 12 small seismic events reported by various organizations. So we look at the IMS station, nearest IMS station called Uzrisk in Russia, and about 6 months of data from September through 2018 February. We look at those continuous data and try to detect small event by using nowadays very popular method of waveform cross correlation using the template event. So we were able to detect several events on top of reported event, also some dozen events which are very small. So about 14 events were located, and you can see that on the scale here, on the left map, that on the bottom there's 6 or 7 stars with nuclear test locations, and then about 14 events scattered around. And once we use the waveforms of slow-moving LG waves on a continental crustal path, we're able to locate very close together. So total dimension is only about 700 meters. This whole 14 event we located initially within about 20-kilometer range become about 700 meters. So these are cases of regional observations and how we use IMS data through vDEC. So I appreciate those support. Thank you very much.
Thank you. So now I would like to invite Professor Wolfgango Plastino to share his experience.
Oh, you want that? Okay. So first of all, let me thank the IDC and IMS director for giving me the opportunity to introduce our experience in the framework of DEC. Especially, it was and it is a powerful tool because we introduced this opportunity for our students at different levels, bachelor and master level and PhD level. Now it's my pleasure to introduce our activities specifically in two PhD programs by two PhD students, Alessandro Longo and Stefano Bianchi, how reported here the network related to radionuclides. So this is our activities actually. And the left is particulate network and the noble gas. I will show some recent paper that we published and give you, of course, a brief introduction for each one. In this paper, we analyzed the problems related to near and far fields. So in the source receptor, the problem is, and atmospheric transport modeling is, the problem is to characterize, of course, the signal and the sites of the possible size of the source, the amount of released radionuclides after a nuclear test. In this case, we focused our attention looking into a noble gas xenon that's generally used for CTBTO purposes, and another noble gas, radon, specifically radon 220. Of course, looking to its daughter lead 212. The reason is because radon is a real local signals in the IMS station, and of course xenon may be produced by a nuclear power plant as well from isotope production facilities. And in that papers, we analyzed the different behavior of these noble gases in the IMS station and giving, of course, the possible interpretation to characterize the near and far field. In this other paper, we analyzed the beryllium-7, generally used for study the atmospheric dynamics, specifically to characterize the tropopause folding and the xenon once again. And in that case, we observed the different structure in time series of two radionuclides in the IMS station. Specifically, we observed that xenon generally has a pink noise structure, and beryllium is different. So you know that beryllium is different in terms of source production because it's a cosmogenic isotope. Xenon is an anthropogenic one, and the difference is also related to because the dynamics in terms of transport of both radionuclides is different. These new papers by Stefano Bianchi, we analyzed the beryllium two cosmogenics, beryllium and sodium-22. And the reason is because in the previous one, the comparison was between cosmogenic and anthropogenic radionuclides. In that case, we had the idea to test the behavior related to the two cosmogenic isotopes. And once again, we observed that beryllium has typical relationship with the meteorological, specifically with the atmospheric pressure. But sodium-22, that also cosmogenic, has no relationship. I mean, it has no cross-correlation with the atmospheric parameters detected at the AMS station. The last one that I show you is a new approach, methodological approach, using empirical mode decomposition. So the idea is to study beryllium-7 once again, and studying for a period of a solar cycle, so 12 years, to, of course, characterize all possible variation related to the cosmic rays production. And in that case, we emphasized some characteristics that I will show in the last slides. The next one is only a flowchart giving the idea of the model that we use to try to discriminate in the time series the trend, the periodical component, the residual component. In that case, our cross-correlation with the meteorological parameter are performed on the residual time series. And I will show also the feedback that can have in the event screening categorization for CTBTO. To give an idea, this is the adaptive trends that we obtained for the station, 28 station that we analyzed. You can see a black line, a horizontal black line that separates the northern hemisphere to the southern hemisphere. And you see also the years from 2003 to 2016 for our analysis. You can observe that we have the different trends year by year for each station, and of course differences between the northern and southern hemisphere. This is a typical characteristic that we need to characterize also the dynamic in time of the trends, because this is not a snapshot, and that we can, of course, consider similar year by year. It's much more clear if we focus, for example, for the annual component. So generally, in the environmental parameters, there is an annual component. This one, for example. This is the annual AMF for 28 station. And once again, there is a separation between the northern and the southern hemisphere. This is a clear evidence that also if you look the typical component in the time series, so 1 year component, is different in the amplitude side by side, so, and also in time, because if we look at a specific station and moving on the horizontally, so in time, you can observe that we have changes in this component. This is crucial when we analyze the data. And indeed, when we analyze the outlier, this is the feedback with the event screening categorization. An outlier is a typical signal to to suppose or to have a suspicious that a violation of the treaty occurred or not. This is the probability occurrence for beryllium for each station that we observed. The different color if the outlier is lower than -3 sigma or higher than 3 sigma. This means, of course, that each station has a specific history, a specific behavior. This is important to characterize, in this case, for beryllium, for, of course, atmospheric dynamics, but it's crucial, once again, if you're looking, for example, for xenon or other radionuclides marker for a nuclear test. So finally, I will show in the last slide the correlation between beryllium and cross-correlation between beryllium and temperature. In that case, you see the station, and in the vertical black line, once again, separate north and the southern hemispheres. And you see that we have now a clear, behavior in terms of typical relationship between beryllium and temperature. This may be a good feedback with PTS. Maybe that this strange pattern in terms of cross-correlation may be related to the filters or in the specific station or in the technique, I mean, in terms of environmental sampling of differences between filters and filters in each station that can affect, of course, such type of results. So thank you for your attention.
Thank you very much. I know that the audience have many questions. We don't have much time, so I would like to propose that we will take maybe 1 or 2 questions, and then during coffee break, you will have a chance to approach our panelists and have some individual discussion. So if there is a question.
Well, a question to all the panelists. What you have in common is the use of vDEC data. And maybe you can give concrete suggestions for improving the vDEC service of the CTBTO.
Thank you very much. Okay.
Can I talk then? If there is anyone in the audience from IDC or IMS, I would suggest that if we have anyone sort of point of contact to interact our sort of findings in some of the cases where we analyzed the data and found out that some of the response of the instruments may not be correct, and we like to interact with the IDC staff to see how we can give feedback on our findings.
Okay, thank you very much.
Yeah, actually, I can second that. It would be important if there, by any chance, was room at the IDC to accommodate perhaps like one person in charge of the vDEC database on a sort of a permanent level. I think that would be really helpful, because I believe at the moment that responsibility is sort of shared across the board, and I think for researchers who use the IDC products, it would be important to have maybe 1 or 2 people to interact with if there are questions or suggestions. Yeah, I think so.
So thank you very much for the suggestions, and now I would like to conclude this session, and if you have further question to our panelists, please continue the discussions during the coffee break. Thank you very much.
Okay. Are you ready? Panel, are you ready over here? Yes. Good.
All right. I think we're ready to get started here on the panel. We have a few more people still looking for seats as they're coming in. Let me introduce myself. My name is Tammy Taylor. I am the director of the International Data Center at the CTBTO and co-moderator for this panel on DPRK. My co-moderator is Anders Ringbaum. He'll introduce himself here in a second, and the rest of our panelists. What I wanted to share with you all is if you have the app downloaded, you are welcome to type in questions anytime during this session, and we'll be sure to integrate them into the questions that we pose to the panelists. And with that, I will hand it over to you, Anders.
Thank you, Tammy. So my name is Anders Ringbaum. I am a research director at the Swedish Defence Research Agency, and I'm proud to be here to moderate this very nice panel. And I will be actually both moderator and also panelist. You will notice that. So here we have with us today, we have Professor Brian Stump from the Southern Methodist University in Dallas, Texas. We have Dr. Vitaly Shukin. He's a former head of the theoretical division at the Russian Federal Nuclear Center. We have Dr. Peter Seibert, University of Natural Resources and Life Sciences, Vienna, Austria. And we have Professor Paul Richards from Columbia University. And finally, also we have Professor Jeffrey Lewis from Middlesbrough Institute of International Studies in Monterey.
And with that, the panelists are going to take the opportunity to take 2 or 3 minutes apiece to introduce themselves to you. Anders, do you want to begin?
Okay, thank you, Tammy. So, as I mentioned, I work at the Swedish Defence Research Agency, FOI. I work in an area we call nuclear verification. And at FOI, we develop equipment and analysis methods for CTBT verification, in particular for noble gases. Maybe you heard of the SONA system that's installed in the IMS network, together with also the SPALAX and the mix systems. We operate the Swedish IMS stations, and we run the Swedish National Data Center for CTBT verification, which is maybe the most important thing in this context here. So the DPRK has really been dominating my professional life since I started at FOI. Been the main theme for what we have been doing. Since we are developing radio xenon equipment, we have been equipped the IMS with these systems, but also specifically, for instance, in 2006, when there were no IMS stations installed in the network around the Korean Peninsula. We conducted a measurement together with South Korea and detected radio xenon from that first nuclear test. And we also have analyzed, of course, every test ever since then. Before I finish, I just wanted to emphasize that I think that the noble gas detection technology still very much is under development, both with respect to equipment as well as analysis techniques. And I think we have come a long way since the IMS was originally designed in the 90s, but there's still a lot of things we can do. And I think the DPRK test, of course, has given us a lot of experience on that. So I will stop there. Thank you.
Great. Well, as mentioned, I'm Jeffrey Lewis. I'm at the Middlebury Institute of International Studies at Monterey in something called the Center for Non-Proliferation Studies. What we do at the Center for Non-Proliferation Studies is study non-proliferation, right? We're concerned with creating factual information about the status of nuclear weapons programs around the world, from the United States to North Korea. It's a very unusual kind of institution in some ways, because much of the work we do historically has not really been done in a comprehensive way in civil society. In many ways, we, on a public and open basis, try to do the same kind of work that, for example, an intelligence community might do, so that we can provide information to the public that is an independent source of evidence about situations involving nuclear weapons. So in my particular case, I was motivated fairly heavily by the lead up to the Iraq War, where the United States government had a series of claims about Iraq's nuclear programs that later turned out to be untrue. But it was very frustrating and disempowering to not be able to say anything in terms of civil society that would contradict that. It's also an issue that comes up in issues of nuclear testing. I think there's the famous case where the United States demarched Russia in 1997 over an earthquake. In part based, I think, on poor interpretation of satellite images. So that's essentially the work we try to do. We're not technical ourselves. We are a policy school. We try to be savvy consumers of technical information. And then we try to fuse various streams of data together. So technical work that other people do, interpretation of satellite photographs, creations of 3D models. As I say, we do this for most countries in the world, but I think a lot of our work ends up focusing on North Korea precisely because it is the sort of country that's hard to visit. And so these tools which allow us to monitor North Korea's nuclear programs from afar, I think in this particular situation end up being unusually valuable. Thank you.
So I'm Paul Richards. I've had a career at Columbia University since 1971 in New York. But I began my professional work in England with a degree in mathematics and then became a seismologist in the 1960s at the California Institute of Technology. I was fortunate in 1975 to be asked by Professor Archie of MIT to co-author a textbook on quantitative seismology with him. It's still in print in English and has been translated into Russian and Chinese and Japanese. And I was fortunate again in 2006 when Ola Dahlman asked me to help organize the first of these CTBTO-sponsored science conferences. It was held here in the Hofburg that year, and we helped also with the one in 2009. But now I'm so glad that the work of organizing them is in the hands of the professional staff of the CTBTO. I've taken a couple of leaves from Columbia University and worked in the United States government, first for a year in the Reagan administration, where my specific issue was working on the Threshold Test Ban Treaty, which involves a very specialized aspect of seismology involving yield estimation, and then spent a year in the Clinton administration on the much more important Comprehensive Test Ban Treaty. At the Geneva negotiations, my speciality was involving how to manage issues arising under the CTBT from the use of chemical explosives amounting to several megatons per year on a global scale. Thanks for the invitation to be on this panel, and if you're interested in the future possibility of achieving what I would regard as radical improvements in the detection and location of seismic events, then please come to my presentation at 4:30 this afternoon.
Yeah, hello. My name is Petra Seibert. I'm a meteorologist and university professor here in Vienna. My special interests are a numerical simulation of atmospheric trace substances and also inverse modeling of such substances. And I was early on exposed to the application of this field to radionuclides because the Chernobyl disaster happened in my first postdoc year. And then as soon as we heard about it, we went to the library and tried to fetch all the books and related to atmospheric radioactivity. And so that's how I started to become interested in this topic. And in the year 2000, I came to the working group B of CTBTO, and since then I have been active there. The FlexPart atmospheric transport model that is being used in the PDS is something I have co-developed, and I have also applied our inverse modeling scheme to the Fukushima nuclear accident and to the 2013 DPRK test inter alia? Thank you.
Well, good morning. My name is Vitaly Shukin. I don't know how much I should tell you about my first 20 years of involvement after graduation, because I spent this time for various issues related to the development and testing of nuclear weapon. Yeah, probably I should go at this point to the subsequent time when I joined in 1994, to the negotiation in Geneva, providing technical and scientific advice to the Russian delegation at that negotiation. So if you discover some things which are you not comfortable in the treaty with regard to verification, you could blame me for these things. Then, after that, after establishing the preparatory commission, I joined Working Group B in the capacity of on-site inspection task leader, trying to help in building this very important part of verification regime. I was doing this job till 2015 in this capacity, and also at the national level, I participated in various scientific studies related to ASI and other part of verification regime. Now I have more freedom, being retired, so I could speak more freely on various issues at this meeting, and thank you very much.
I'm Brian Stump. I'm a professor of Earth Sciences at Southern Methodist University, and I thought about, and first I'd like to thank Tammy and Anders for organizing this panel and inviting me, but that was where I started. I thought, why me? And as I thought through this, I thought maybe this was a good way to introduce myself. Maybe one thing is being independent as a faculty member, and that goes back to early on in my graduate career, within months of starting my graduate career at UC Berkeley. Some of you knew Tom McKevely. He came into my office and dumped 6 digital recorders on my desk and said, call this number, there's going to be a nuclear explosion in the Nevada test site, I'd like you to measure the close-in ground motion, so maybe we could do some source theory work. And that was a long time ago. Second reason might be that I took a short hiatus from the university for 4 years and at Los Alamos National Laboratory. And during that time, I was a scientific advisor to this CTBTO or CTBT negotiations for the US team, and that provided me insight into the value of the technologies that we use. Upon returning to the university, my students and I have been interested in fulfilling that request that Tom McKevely made, and that is in terms of understanding the source functions as how they generate seismic waves. But I think because of the negotiations, I became interested in multiple technologies, and so we work in both seismology and infrasound in trying to think about how these can help us constrain the sources of interest. Finally, I'm interested in data, and in the United States, IRIS is an important distributor of data, and I think that the CTBTO as well collects data and distributes it to the state's parties, and I think that's a very valuable role.
Wonderful, thank you. No online questions yet, so we'll start from a list of prepared questions that we have. And Anders, I think I'm going to bounce this off to you first, and then other panelists, be thinking about whether you would like to weigh in on this one. What are the scientific evidence that the 6 announced tests from the DPRK really were nuclear explosions?
Thank you, Tammy. Yeah, I think this is really the basic question, and that's the core of our job here, of course, as an NDC, for instance, which I represent here. So during the years, it has been our job to answer this question to the Swedish government, for instance. So did the DPRK conduct a nuclear test or not? So how do you go about to do that? Well, when doing this, you have to collect evidence, and you have to do it in a way that is unbiased. So you don't have personal preferences or anything going into that process, and that's not easy. So what we have done is we try to set up a set of criteria that all should be fulfilled to be able to say yes or no. So if they're not fulfilled, all of them, we say no. We cannot come up and say maybe, maybe not, depends. That's not the way we can do this at an NDC. So, for instance, we need a seismic signal identified as an explosion. We need a radionuclide ratio compatible with the time zero, for instance. We need to be able to exclude other sources. We need atmospheric transport modeling that fits the explosion time and so on, and things like that. So that's what we have been trying to do. And looking at the tests we had so far, and I'm a radionuclide guy, so I look from the radionuclide perspective, and that's also nuclear explosion. So, of course, let's measure radionuclides. So that's what we are focusing on from our side and try to improve that capability. So in 2006, I mentioned already, there was one detection that we made, and some other natural and means also detected the radioxenon. And then there was this detection also in Yellowknife compatible, in the IMS system, compatible with a nuclear test. So the 2006 test was very important also in another aspect because it was a low yield. And in this case, you can actually fake an explosion by conventional explosives. It was below 1 kiloton, maybe. So it was even more important in this case to really find the proof that the signature was a nuclear signature, and that was possible. So in that case, in 2006, yes, there's solid evidence. In 2009, the yield was a little bit higher. And no radionuclides were measured that we could really confirm associated with the test. So, okay, I have to pass that on to the seismic community here to continue that one, on that one. 2013, we again discovered radionuclides, but that was like 55 days later. But still, we couldn't connect that to the test as well. So for solid evidence regarding radionuclides, there are actually 2 out of 6, in my opinion. Then there are some theories also for the other ones, but they don't fulfill at least my criteria. So that's from my perspective, how I see this. So then maybe we could pass it on to the other panelists. Also, I would like, interesting to also hear from you this, is it possible to distinguish between conventional explosion and a nuclear explosion in a seismic signal at some point or not? Because if you have a low yield explosion, it may be possible to accomplish this with a conventional explosive. So just pass it.
So I think the question really requires an understanding of who you are trying to persuade. Are you trying to persuade a 10-year-old child? Are you trying to persuade a journalist who is doing his or her job? Are you trying to persuade a nuclear weapons designer who might exhibit willful ignorance about the capability to monitor nuclear test explosions? It really is a variety of different audiences. But assuming that there is a willing audience, first of all, that each of these 6 events in North Korea was an explosion, in my view, is best illustrated by certain details of the mix of several different types of seismic waves that are widely detected. Then on the question of whether the explosion had a chemical or a nuclear origin, then you get into some details. And now the question is how to manage some of those details, which in many cases are exceedingly boring, depending on the audience. Are they really interested? And one hopes that they are interested, and one can explore it at many different levels of depth. But it depends on the audience. You can't offer one persuasive discriminant. And there's no silver bullet in this matter. So if one has an unwilling audience, then you sometimes have a difficult task because of the complexity of the mix of technologies. So it is a difficulty, but if there is a willing audience, then believe me, on the 5-minute scale or the 5-hour scale, there is a very clear story to be told.
Very good. Thank you, Paul.
Could I add something? And that would be to echo some of the things that Paul said, but I think, and there's a question of a single-fired chemical explosion where things are detonated over a very short time period and they're fully contained. And then the broader question, and particularly as we think about screening events, delay-fired explosions that extend over long time periods. In that case, I think there are good differences between them. But the non-proliferation experiment, where a large amount of explosives, fully contained, was detonated close to a location where nuclear explosions were detonated, produced almost identical waveforms. But the practicality in the case of DPRK, where we start in 2006 with a very small magnitude event, go to 2017 with a very large magnitude event, in my mind, we quickly eclipse the possibility that chemical explosions would be involved with all of those events.
Jeffrey, you had a comment?
Yeah, I would just say that I find these conversations very interesting because, again, we're so focused on the policy implications of things. We are consumers of this different type of analysis. And I would say, if you're discussing this with a policymaker, there are all the technical issues, which are, I think, fairly persuasive. But what I find is even stronger when you can marry the technical analysis with the kind of comparative and historical work that, for example, we might do. So, I think it's very good for policymakers to know, for example, that you're not always going to have a radionuclide signature. It doesn't mean it wasn't a nuclear test. It's just that's not a thing you can count on having. And so we often do quite a bit of work where we try to compare the suite of technical judgments that have been made with historical cases. So, for example, my dissertation actually was on the history of China's nuclear weapons program. And so one useful thing one can do is ask, particularly as North Korea has moved to higher yields, do we believe that's credible? Well, you can ask, well, where were the Chinese after 6 tests? And so, one of the things I love about this conference and I love about this work is we have all of these different sources of information, which we can then fuse into, I think, a single probabilistic judgment with, I think, fairly high confidence.
Okay, thank you. Petra.
Yeah, I think the most interesting case in this respect is 2006, as it was still in a magnitude range where we could not be totally certain that it is really a nuclear explosion. So it really depended on the radionuclide signal. And the signal was detected at a relatively far away station at a magnitude that is within the range of the background. So we had also to use, in addition, atmospheric transport modeling. And because the distance is so large and there is a mountain range in between and so on, also the atmospheric transport modeling wasn't perfect and couldn't be expected to be perfect. But we could at least exclude that the Chalk River facility could have been the source of the signal, which is causing most of the background in the Yellowknife station. And also there was the interesting feature of having multiple samples with xenon detections and a characteristic double peak. And this shape was reproduced by the atmospheric transport modeling. And so that gave us a good confidence already at that time that we really were able to show that a nuclear explosion was the source of the detected radioactivity.
Thank you. Vitaly, did you?
Yeah, thank you. Thank you for giving me the floor. Yes. Let me continue along the line indicated by Anders. Indeed, this is the point of possible or eventual concern, the absence of radionuclide detection. I am less concerned with this difference between chemical and nuclear explosion in terms of seismic signal identity, but on my view, detection of relevant radionuclides is the only final proof for nuclear nature of the event. However, having said this, I should add that IMS and IDC are not the only tools in the hands of the future organization. We have OSI part of verification regime. And even in the absence of radionuclide detection by IMS IDC, we could get finally the right answer conducting the OSI. So I am, let me say, I am more optimistic with this regard. Thank you.
Thank you, Vitali. I just wanted to, since we are talking about the absence of radionuclides here, I just wanted to say that this is really a thing we have learned, I think, from this test, that originally the network was designed with this 40-station network for the noble gas, and that was based on a source term of like 10 to 15 becquerel. That's 10% from a 1 kiloton explosion leaking out in the atmosphere, roughly. And that has not been the case, except from the first test. Also I heard that there has been other talks here indicating, for example, some old Russian tests that there were like 10 to 14, maybe 10 to 13 becquerel or something like that instead. So we need to rethink, I think, the density of the noble gas network. We have learned, we are still in a learning process, and I think that is a key lesson for radionuclides, and that because there are certainly new technologies, new possibilities to improve on those measurements. That's, I want to say that. Okay. So I go on? Yeah. Okay, so if you have no more on that one, I will go on to the second prepared question we have here now. And this, well, we go on with the discussion on measurements. Are we fully satisfied with our knowledge of DPRK nuclear tests based on information from the IMS, I mean, such as science base, source receptor, and modeling capabilities, for instance? And Vitali, could I start with you on this one?
Thank you. Thank you very much. Since I contributed in some sense in the creation of this prepared question, let me say a few words on this issue. First of all, what kind of satisfaction are we talking about? Of course, any scientist could not be fully satisfied with any knowledge about the nature. And with this regard, of course, we would like to know more about this interesting event. Let us limit themselves with verification-related aspect, verification-related responsibilities of future organization. With this, I should make a caveat saying that the current organization does not have verification responsibility, and only after entry into force we will address this verification issue. The second caveat here, or point perhaps, is that we are considering how we call it, announced or declared events which were declared as nuclear explosion or nuclear explosive test. And this has some unavoidable impact at our knowledge, at our assessment. Also, we try to be unbiased here. So with these two caveats, let me consider the whole situation. Also, Anders addressed this whole picture. Again, we have 6 events, underground events, well detected, on my view, by international monitoring systems. There is no doubt on this. So we could be satisfied with this detection related responsibility. As to location, we also have, on my view, very good results considering the link with on-site inspection if necessary, because the accuracy or uncertainty in establishing location of these events is less than required by on-site inspection. This is much less than 1,000 square kilometers, and I mentioned not more than 50 kilometers in any direction. So about location, I think there is a more or less satisfactory situation. About screening. Screening is a very important part to avoid mistakes. And here situation probably is less clear, at least for me, because my knowledge is that not all the seismic events had a very clear pattern of explosion. So perhaps there is a room for further improvement with this regard, for further improvement of PTS and future TS capabilities by developing the issue of source, development of screening criteria, and this is one of the rooms for further improvement. About radionuclides, we addressed this issue already. Indeed, we have just two clear detections of level 3. The first one is highly likely the detection of relatively prompt venting, because just of a relatively short time of traveling from the point of explosion to the radionuclide station. But we have just one station and we have just one radionuclide. So indeed, we should also we should keep in mind that it was a relatively early time of the development. The organization didn't have the full set of stations to be monitoring this type of signal. So now situation is slightly better. But again, we didn't have a detection of level 3 for the second situation. So we should be cautious with this issue. And perhaps we could address again the same question, whether there is a room for further improvement of our organization now and in the future. For example, we could consider whether the density of current stations, and this decision was taken a long time ago, whether 40 current stations which are capable to detect noble gases is the best solution, taking into account experience from here. So in principle, there could be just missing release. Another issue is, or another option here, is that there is a very high level of containment, very good containment, and should we consider this option also, I think we should pay attention to this aspect and be prepared for a really high level of containment scenario. Again, this is a room for subsequent on-site inspection application with this regard. So my conclusion is that for the time being, we could be satisfied with the current capabilities with all the caveats made. For the future, we could develop further, and we should develop further these capabilities, developing not just the own capabilities of future organization, but also addressing such aspects as national operating facilities, national technical means, and perhaps I have more freedom to speak about this now, perhaps even some modification of verification system after entry into forces, if states agree on this. I could recall with this regard that during negotiation in Geneva, the Russian Federation suggested to consider option with inclusion of aerial sampling, aircraft-based sampling, in addition to ground-based, and perhaps this option would be reconsidered in the future. So thank you very much. Probably I was speaking too much on this issue, and the others could express their view.
Thank you, Vitaly. So does anyone else want to chime in on this one, or should we?
Okay, we can move on. We've got lots of questions streaming in from the audience, so I'll take the first of those for us. What improvements to the monitoring regime are necessary to definitively say that there has been a treaty violation? And what can CTBT laboratories and national data centers do to realize this?
Perhaps to begin with a little history, when the terms of the treaty were being negotiated in the mid-1990s, the technical goal articulated by the friend of the chair, Peter Marshall, was to have an international monitoring system that could reliably do the work of monitoring down to 1 kiloton. So here we are, more than 20 years later, with a lot more practical experience, and the system that was built, even though it is not absolutely complete, performs admirably better than its original goal. So that's one platform upon which one could expound at greater length. Given the nature of the question, I would forthrightly say that a comprehensive system with a definitive capability is that really a reasonable goal? I think that as a scientist, that's perhaps not for me to judge what is a satisfactory capability, but to require perfection seems to me absurd.
Thank you. Jeffrey?
You know, working in the policy sphere, I think is useful in tackling this question, because ultimately the decision of whether an event is a violation is going to be a political decision. You know, what the monitoring system can do is identify events, and if the treaty were in force, there would be the possibility of an on-site inspection. But you know, when I teach how the CTBT might work to my students, you know, I always point out that at least the diplomats I interviewed who helped craft the on-site inspection procedure always assumed that if a country conducted a test and an on-site inspection was requested, even if the inspection was authorized, that country would refuse. And that's fine, because if you ask for an inspection and they say no, you have your answer. Mm-hmm. So, you know, from my perspective, I think the international monitoring system is incredible. I would always support efforts to make it stronger. But I think that we sometimes underestimate how unlikely it would be for a country to conduct a nuclear test of you know, a kiloton or more, and have any chance whatsoever of that not being detected. And so I think that's a tremendous improvement in our security situation, because if you are someone contemplating that, I think that your confidence in getting away with it is at the moment very low.
Okay. Yes, Brian.
I'd like to follow up something that Vitaly said, and maybe I can say it because I'm a professor and I'm not part of the treaty necessarily, but when the treaty was negotiated, there were a set of monitoring technologies. And I think since 1996, there have been substantial changes in publicly available kinds of data that has some bearing on the treaty, such as overhead imagery. INSAR, for instance, certainly needs experts to be able to interpret those kinds of data, but they're incredibly complementary to earthquake locations, to explosion locations, to understanding deformation, possibly in and around the explosion, that has bearing on our assessment, and in particular, our ability to locate and screen events. So that might be some suggestions I would make.
Got it. Thank you very much. Petra?
Yeah. Already the treaty foresees an option to increase the noble gas network from 40 stations to 80 stations. So to double the number of stations by making all particulate stations also noble gas stations. And I think there are good reasons for seriously considering this option. Why? It has already been mentioned that from what we have seen in the DPRK tests, the actually occurring atmospheric releases, first of all, in most cases, it's only xenon that we have detected. We have only one case where particulates were detected, and that is a case where we don't even know whether it came from a nuclear explosion or what was the type of source. I'm referring here to the May 2010 event. And on the other hand, yeah, these very low xenon emissions, they have to be found within a background, a civilian background. Maybe we can see the figure number 6 now that I prepared. So that makes it even more difficult to clearly identify. I am not up yet. Number 6, if possible, please. Yeah, we see it here, but not yet there. Oh, here. Okay, very good. Yeah. So you see that over large parts of the northern hemisphere, we have on the order of 1 millibecquerel of xenon 133 per cubic meter on the average. So if we have a higher density network, it means the transport distances to a station are on the average shorter, and that means less dispersion, and that means a stronger signal, and that means more likelihood, first of all, to have a characteristic signal that sticks out from the background, and secondly, also more accurate atmospheric transport modeling. So I think that is something we should really look at, and then also technology involves, and better xenon monitors are underway, which may have better detection capabilities, especially for different xenon nuclides, which would be very helpful. So there is room for improvement that I think should be considered.
Thank you. Back to the questions.
Yes,
screen.
so we have a lot of questions from the audience. Just can get back the. Okay, we have it here. So we have a question here on crowdsourcing. What are the various panelists' views on the use of crowdsourcing for verification of the CTBT? Will this ever be a useful area, or will technical and policy restrictions not make the use of things such as social media and other crowdsourcing concepts realizable? So, what do you think about this panel? Yes?
Yeah. So we're quite excited about using crowdsourcing in various ways. I noticed that the U.S. Geological Survey does this, where if you look at an event, it asks you, did you feel it? And you can sort of rate the ground motion that you experienced, which someone rated one of the North Korean tests once, and I think that raises some questions about whether that system is as reliable in verifying people's location. But quite seriously, there are a number of tasks that I could imagine a crowd being useful for. One of the ones that we're exploring, and Grace Liu was on a panel on Monday evening, and she runs a project for us called Geo for Non-Pro. And one thing we would really like to do is build very large data sets to enable machine learning. And if someone is going to be testing a nuclear weapon underground, if they're digging a tunnel, there's going to be a large pile of spoil in front of that tunnel. We would love to teach a machine to be able to go and look for piles of spoil all over the world, so we would have some idea of potential test sites. That's a very tedious task to create such a database. That's the kind of thing a crowd would be really quite good at. We're not doing spoil piles, we're doing something else, and I'll let Grace reveal that in its time. But there are real things for crowds. In terms of social media, it's a slightly different question. But yes, I think it was yesterday, my colleague Anne Pellegrino, she talked about some work we've been doing characterizing the Russian nuclear test site at Novaya Zemlya. And social media has been incredibly valuable because, the reality is people on deployments take photographs and they put them online. And it's extremely helpful to be able to understand the organization and arrangement of a test site. Now, I think that would be very hard to imagine asking an international organization to do that sort of work. And this gets to a kind of hobby horse of mine, which is the last thing I'll say. which is an unusual feature of the CTBTO, is that there is both the provision for the international monitoring system, but in the instance of an on-site inspection, one can also bring national technical means to the table, right? I've already started by introducing myself by saying I've been unhappy with the way that national technical means have sometimes played out. But civil society now has its own technical means. And so I think an interesting challenge for the CTBT going forward is how can it find a way to integrate information from groups like ours? Because, you know, we may well find some person who on their, you know, whatever the North Korean equivalent of Facebook will be, you know, who posts, well, I'm off to do a nuclear test. You know, that's evidence. We've seen that kind of evidence be used in the MH17 investigation. It could be of use to the CTBTO, but I think the important question is going to be how do we bring that information in a way that parties are comfortable with.
Thank you.
I might turn it around, maybe backwards, but even though what we do is very serious business, and it's very important to provide states parties with the information that the CTBTO develops. There's also a component, I think, in terms of education and outreach and communicating to the public in ways that they can understand, in terms that they can understand, so that they can make their own judgments about things. And I wonder if this kind of media plays a role in that. Carefully done.
Well, I just had a comment on this also. From the NDC perspective, of course, it's, I mean, looking at the network right now, it's really, we have certification procedures, there's a lot of data authentication procedures, so there are like technical, legal aspects going into this as well. And if you have crowdsourcing, then I guess that could be problematic. So we have to find ways to make the data usable in this context, because otherwise it would just be rejected as, well, we can't trust this source. So that might be a big problem in this context, I think, maybe.
All right. Oh, Vitali.
Thank you. Very quick thing that was not mentioned with this regard, as I understand. Besides our own efforts and besides general efforts by the PTS, by the organization, we have very specific part of the PTS, the unit which is responsible for interaction with media. So perhaps there is a room, besides advertising the excellent PTS capabilities, excellent organization capabilities, to try to react promptly to completely wrong things which might mislead the community.
That's a great recommendation. So having public information ready to flow when there's erroneous information flowing. We'll stick with the popular questions you all are asking. There's one that jumped way to the top of our list here, and it asks, how much could an on-site inspection of Punggye reveal now about the yield and design of all the previous tests?
Just to be clear about the question, I don't think a specific goal of an on-site inspection would be to address those questions. So. So it's not entirely fair to assess the success or otherwise of an OSI in the terms of the question. Was there a treaty violation is the issue.
Is the simple question, yeah.
Yes. So.
Okay. Simple
okay.
enough.
Since my previous responsibility was to develop this part, or to help to develop this part of OSI verification regime, let me address this question quickly. Well, Paul, you are right. Indeed, the sole purpose of OSI is limited by the treaty. This is a famous paragraph 35 in the verification part of the treaty, which says the sole purpose of OSI is to clarify whether a nuclear test explosion or any other nuclear explosion has been conducted in violation of Article 1 of this treaty, and to try to gather, to the extent possible, any facts related to possible violator. For underground events within the territory of the state party, in particular, in the case of DPRK, on-site inspection, if any, would be limited with just these two tasks to identify the nature, to clarify the nature of the event, and in that way to clarify whether there was a violation. And, well, it is not clear for me whether there will be the real need to look at any other possible violator for this specific scenario. Any possible violator is much more relevant to the event beyond the national borders, like ocean. The inspection formally will be limited with its own purpose. In principle, it could shed the light on the issue of possible yield and even design, detecting some specific features related to the event. Of course, for the yield, such things as visual observation, estimation of underground cavity, and other relevant observers could provide useful information. But again, this is not the purpose of ASI. As to the design, yes, if the on-site inspection discovers specific radionuclides, or specific materials, not just radionuclides, actually plutonium is also radionuclide. Yeah. There might be some information related to this issue, but this is not the responsibility of organization.
All right, let's move to the next question that we have.
Yeah, so let's go on with the discussion on source physics and so on. Do we sufficiently understand the source physics of underground explosions in order to provide a basis for interpreting all observed signals? I mean, if not, where might there be additional work to help constrain the observations? And I think, Brian, if you want to.
I think that's an excellent question, because I think sometimes we make intrinsic assumptions about a model that we use to interpret the data. And this is my personal belief, but that we don't then incorporate the errors, the possible errors in the model into our estimates of the phenomena that we're trying to study. And I think that is the case for the explosions in North Korea. And you could think about, from a seismological perspective, the effects of the topography, the actual material the explosions are detonated in, and how they respond from the nonlinear to linear regime. We debate the depths of the events, as well as broader interactions with the free surface, because there are nonlinear interactions with the free surface, all which go into the generation of those regional and teleseismic observations. There are a wide variety of interpretations of the sources as a result of those things, and so yes, I think it is an open question. One of the exciting things to me is that at least when the treaty was negotiated, I didn't perceive that infrasound would play a very strong role in underground explosions. But yet, through this sequence of 6 events, we've seen infrasound that accompanies some of the events, certainly reflects the time-varying nature of the atmosphere, but if that can be unwound, it does provide some information about the coupling in the region right above the explosions. And so, as a result, I think there is some good work that can be done in helping us resolve the source models and maybe refining our estimates of the sources. And I think it was both Vitaly and Paul mentioned the discriminants in BMS, for instance, and improving our understanding of the large MS values that have accompanied the events might be a goal.
Okay, thank you.
So I'd agree that although we don't need perfection in our knowledge or our monitoring capability, we should definitely work toward it. And in that regard, I would certainly appreciate a better understanding than I now have on what happens in the immediate environment underground of the release of those enormous amounts of energy represented by nuclear testing in the only country that's been doing it in the present century. Huge amounts of energy is released in a millionth of a second that vaporizes rock, that melts the rock, that cracks the rock, that moves blocks around. And then in this complicated environment, somehow, although 98% of the energy may be consumed locally, 1 or 2% gets out into seismic waves. And that turns out, according to a number of reviews, to be one of the most effective monitoring technologies. So I don't claim to fully understand all of that complicated process. Perfection is not yet achieved, and it would be good to work towards it. But the consequences for the work that needs to be done today of lacking perfection, in my opinion, is minimal.
Thank you for that. Brian, back to you.
Can I add? It has to do with the meeting we're at, the Science and Technology meeting. I would think this is an excellent environment for the scientific community to exchange ideas on these issues.
Yes.
And I guess I would encourage the continuation of these kinds of opportunities for people like us and in the audience to come together to share ideas about some of these questions.
My sincere hope as well. We have one really hot question that rose to the top of the list, and then I have a favorite question that I wanted to ask from the prepared questions. And then I guess we'd like to hand it over and make sure the people who don't have the app have the opportunity to ask questions or make comments from your expert position as well. So Anders, why don't we take that top burning question and then I'll ask my favorite one.
Okay, so we got the question here that's on the top. That's from Brian. Yeah. For the 2 DPRK tests detected via radionuclides by the IMS, would an OSI still be warranted? So,
I mean, I think the answer is no. They're not the DPRK is not a party to the treaty, and in any event, the DPRK is not denying that they conducted a test. So
it seems like a bit of a trick question because we can't move into OSI space until they are a part of the treaty.
Yeah. So I mean, yeah, okay. It would be a fun exercise.
Yeah.
And probably contribute to the capabilities.
Good. Vitaly's hopping behind you.
Yeah. Okay.
Yeah. Thank you for giving me floor again. Well, first of all, this is a question actually for 2 sides. This is a question for state parties, which should request OSI, because OSI could be conducted only in the case of getting a request for at least one state party. The second aspect is, or the second addressee, or the second player here is the Executive Council, which should take a decision on the inspection. So it depends very much on these 2 main players. If you ask me, for example, is it sufficient, on my view, to leave without on-site inspection and hence express the view that there was a clear violation in such case? Well, as I said, for the first case, we have just 1 station and 1 radionuclide. So my curiosity is higher than the information available here, and I would prefer to have more information, including possible use of OSI. The second case, again, I said that we have a so-called control release. Well, perhaps the situation is slightly more convincing and I assume that it would be difficult to get approval by the Executive Council for such a request, if any. But again, I envisage that many countries might come to the conclusion that there was a violation. This is actually what the state parties to decide whether there was a violation or not. Thank you.
Petra?
Yeah, I think we should really understand that an on-site inspection is not to gain somehow more information about a test. It is to verify whether a test has been conducted or not. And North Korea has never denied that they conducted a test. On the opposite, yeah? They want the world to know that they are able to carry out nuclear explosions. So I don't really see any justification in the case of those two, but also of the other DPRK tests.
Okay, good. Yes, Anders.
I just wanted to add, okay, for the first test, so the IMS detection alone, I don't think is enough to prove that there was really a nuclear explosion at that time. I think the national technical means that were added, they added the proof. So in combination, yes, then you don't know. If we also add that information, then we could say that yes, they did an explosion. The second one, I think that also that you don't need to do an OSI for that one.
Okay, good. Vitaly?
I would like just to add that at a certain moment in our OSI community, we had a discussion on this issue. What are the prerequisites for launching the OSI? And some part of our experts argued that only the radionuclide detection would be sufficient to launch the request. And without radionuclide detections, there will be no room for submission of the request. There was their private view, but as I understand, it would be also their state view. Other people argued that if we find radionuclides in a convincing scenario, various types of radionuclides with various ratio, consistent with seismic detection, there might be no need for a science state could decide based on this information. So this is the open issue, and again, the state will decide after entry into force.
Okay.
And it will come.
Not exactly clear-cut in terms of criteria. Okay, so this is the question that I referred to as my favorite question from when we were working in preparation for this panel discussion. And I'd like to direct it first to Paul, but anybody may weigh in on this. Oftentimes we see really absurd, sensationalized media reporting regarding the DPRK, and it really warrants some kind of a response from the technical community that refutes some of that on the basis of real science, real information. It's really difficult for us sometimes as scientists and engineers, technologists, to get inclined to be engaged in these false reporting activities. And so, Paul, I'd just really like to hear your opinion on what we should do about that.
Well, it is a question that I would like to address. Perhaps an example will help us. A week or so ago, I came across a report in a London newspaper with a big headline to the effect people were really terrified close to the border between China and North Korea about the occurrence of some type of massive seismic event. It turns out, on reading the text of the article, that this was with reference to something less than magnitude 2 that, from my own knowledge, I presume was yet another aftershock of a nuclear test more than a year earlier in North Korea. But the idea that people in that part of China had felt something and had been terrified by it and that had thought might be an additional nuclear test explosion was wrong on so many technical levels. But of course that headline was in the paper to sell the paper. And so we all have our priorities, and I will be completely ineffective in my own specialized research activities if I spend my time on trying to address yet another story, especially in the context where perhaps there would be some level of entertainment in a London journalist seeking to make a fool of some elderly professor who's worried about something. I mean, that helps to sell the newspaper too. So I would love to have a group of people who are much younger than me, who might find it themselves of some interest to correct erroneous factual stories that occasionally appear in the newspaper, both for purposes of trying to prevent such stories from appearing, if they can be effectively shown to be foolish, by a community that a newspaper must pay more attention to than to people like me. So, a long answer, but it is, I think, a growing problem when newspapers seek to build an audience, whether it's a newspaper or a cable news channel. And in some of these issues, I'm reminded of the phrase, "Don't wrestle with a pig," because you both get dirty and the pig loves it.
Any other thoughts from the panel on that one? Brian, were you raising your hand?
Well, I was just thinking as scientists and engineers, I agree with Paul, but in scientists and engineers, we do have some responsibility for communicating in ways in which the public can understand us. And in some sense, that is a dialogue. It's not a single interaction. And each of us as individuals have to decide how that is done. But I think it's maybe one of the more important things that all of us have in life, because we see not just for the CTBT, but questions about things, global warming. In the state of Texas, we've had these great debates about induced earthquakes and the impact on oil and gas. And I think if we don't engage in some way in the conversation, they can go in very strange directions.
Thank you. Thank you. I think let's turn to the audience that may not have the application or anybody who wants to offer a comment to us. We have 3 people with microphones. We need one right here in the front.
Okay, thank you to give me the chance to comment or ask. First, I'm Yusri Abu Shadi. Maybe some of you heard about Abu Shadi because I was responsible of the inspection in North Korea for many years. In fact, it is a country other than my national country and Austria where I spent my most of time during the inspection. So I think I know very well really North Korea till 2009 and following really all the events. First really about the doubts about North Korea detention or explosion, I strongly believe they had capability even before 2006. Sure, in 2006 it was a plutonium explosion. Maybe it was the first explosion, that's why there was a problem of confirmation of that. But sure, they continue, and to my calculation, these 6 explosions cannot be plutonium bomb. And because they don't have enough, actually, plutonium. And that was one of my trouble with some estimation from especially the United States in the past, in the 90s, when they were confirming that North Korea had the capability for 1 or 2 bombs. At that time, I don't believe really they had that capability at this moment, because they started the safeguard quite early in 1992, and there was not enough chance to accumulate plutonium. Now my question actually to the expert here is related to the detection of the type of explosions. As I said, I don't believe really that plutonium continue. At certain moment, sure, they switch to what I think probably enrichment, probably thermonuclear, but on a smaller scale. So I would like really from your experience really to comment on the type of the 6 explosion done by North Korea. Thank you.
Thank you.
Boy, everybody's looking at me. You know, one of the interesting things about the CTBTO is because really the only question is, was there a nuclear explosion or not? Questions about nuclear design information they exist elsewhere. And that's an interesting, it's an obvious division of labor, but sometimes it matters. So for example, the first nuclear test, which was extraordinarily small for a first nuclear test, was a little bit of a puzzle. And I think our judgment is that North Korea tried to build a compact device without testing, which is something that the US intelligence community had always said if a country did that, the result would be a disappointing failure. And North Korea tested what I think was a disappointing failure. So trying to marry this information together and provide a comprehensive picture can be quite difficult. To answer the question very specifically about the 6th nuclear test, if one reads what the North Koreans have said carefully and one looks at the experience of other nuclear powers, particularly the Chinese who shifted from HEU to plutonium, the North Koreans are going in the other direction. My strong sense is that what North Korea is doing is testing nuclear weapons with what are called composite pits. So they don't use either plutonium or HEU, they use both. And that's a relatively efficient way to stretch a small stockpile of plutonium. So my expectation is that the last test did have a small amount of plutonium in it, but that the pit was filled out, as it were, with highly enriched uranium.
Anders, did you want to make a comment?
Yes, I mean, to really get evidence on the type of explosion, you need nuclide ratios detected. And the ones we have, in 2006, the ratios that were detected, actually, you could see that they were absolutely more compatible with plutonium explosion than uranium. So that in that case, we also have some clear facts, I think. That's the only measurement we have. And then in 2013, it was detected so late, so you couldn't say anything about that at all because of a later release. Now, again, then we have this question of fission fusion that everybody asked after the last test. I think we have looked into this a little bit. Would it be possible to distinguish these two types with some ratio? It might be during very, very special circumstances if you have a really quick release and so on. But it's still uncertain because it depends also on nuclear data libraries, which are different. And it might even be that we have to do some more cross-sectional measurements to really be able to pinpoint that. So it's unclear, I would say, in my opinion.
Okay, no one else is leaning forward. Next question, right here, 4th row, center. Keep your hand up so she can see you. Thank you.
Thank you for giving me the floor. I'm from Korea NDC, Kigam. I have a very specific question related to cavity radius developed by nuclear test. I'm wondering if there is a trade-off between scaled cavity radius and depth of burial for all kinds of rock type at the source. How do you think about this issue?
Brian?
So that perhaps goes to Brian or me.
Go ahead, Paul.
So in general terms, yes, to execute a series of tests, let's consider a thought experiment, all of the same yield at greater and greater and greater depths. subjects the immediate environment of an explosion to larger and larger pressures because of the overburden. And so one would expect the cavity to be smaller. So that's a technical question. If we go into greater detail, it would take a lot more time. I appreciate the question, and it's important for those who wish to develop a good physical model of an explosion to provide detailed answers to good questions like that. So on the one hand, yes, I'm glad to have the question, and it's well worth discussing within the technical community. But let us never convey the concept that a total and complete answer to such technical questions should inhibit progress in a major nuclear arms control initiative. So I'll just leave it at that.
Right.
And that question bears on a question of yield and yield estimation, which is the state's parties, and in some sense outside of the screening criteria that the CTBTO requires. But it is, I agree with Paul, it is worthy of discussion. I would note that experience with explosions in granite is maybe not as robust as others. And so understanding the material properties of those granites is important. And then I would add that it's a place where synergy of different technologies may play a role, because you're talking about the role of the source function for seismology, but it's also related to the source function for the infrasound. So as you move away from the free surface, you may see a complementary effect in the atmosphere. And so the one thing that I think we don't spend enough time talking about is how we tie our technologies together in maybe a broader understanding of the source functions.
Perhaps I can just add that a detailed experiment that addresses your technical question was conducted in Kazakhstan in the 1990s, when one of the deep shafts that had been prepared on the Semipalatinsk polygon for a large underground nuclear test that was never executed before Kazakhstan became an independent country and totally stopped the conduct of nuclear testing and provided leadership towards a comprehensive test ban treaty. So in that dedicated hole turned over to the technical community were conducted 3 explosions of the same yield using chemical blasting agents at 550 meters, 25 tons, at about 300 meters, 25 tons, and very shallow. I think it was about 50 meters. And absolutely, it just showed that the strength of the seismic signals from that sequence of 3 explosions, all of the same yield, resulted in much stronger seismic signals for the more shallow explosions. And indeed, there's a good theory, well documented, that the strength of the seismic signals from an underground explosions is more or less proportional to the size of the cavity. So the idea that the cavity gets bigger and bigger and bigger for the shallower and shallower tests, or the way I explained it a couple of minutes ago, that the cavity is smaller and smaller and smaller for the deeper tests, is pretty thoroughly understood both theoretically and in practical terms.
Vitaly?
Just 2 small things. The first one, following the Paul point, indeed this is a very important issue, this relationship between the depth of explosion and seismic signal or magnitude. I remember when I started my activity, we used very simple relationship between the yield and magnitude, just one parameter. Now we have much better assessment taking into account the depths, and we have, I think, better understanding of DPRK explosions taking into account the estimated depths. Also, depth is actually not known, but we could come with some guesses on this issue. So we are improving our understanding. Another aspect with regard to the size of the cavity. We didn't address this point today. There is another parameter or another issue, decoupling. Beside the cavity created by explosion, we have the initial size of this cavity where we place our explosive device. And the coupling factor is very important, again, in terms of interpretation of our seismic data and also some other data. So let me conclude that we have a lot of things to be done by scientists here on this specific issue, both within the PTS and in the broader community.
Okay. So we're down to about 8 minutes before we go to lunch. I'm sure everybody's hungry. I had a text with a question, and I asked Anders if he could answer this, and he's going to make an attempt at it. This was brought up several times today. Petra may want to comment as well. So in the absence of nuclear tests, what would you propose to test the need and performance of a more dense noble gas network?
Okay, so what do we need to do to detect when we want to detect something? We need to locate the source, we need to characterize the source and detect it, of course. So you need to improve these capabilities, and a denser network will help, of course. In particular, you want to be able to have multiple hits on stations. That will give you a much better location possibility than if you have one station only detecting the source. And today we have quite a lot of sources in the world that emits radio xenon. We have all the isotope production facilities. A few of them actually are responsible for 95% of the release, as you saw already from the map from Petra before. And we can use them. If we have stack data from them, we can use that information and really improve on all these capabilities. So I think it's no. I mean, we don't need a nuclear test to do that.
Okay.
Yeah.
Anything more, Petra? Vitaly?
Again, on the same issue. And indeed, we have this question with us, whether we have enough sufficiently dense network to detect noble gases at the current point. I remember that discussion at the conference on disarmament, how much station should be capable to detect noble gases within the overall network. And at that time, we came to this type of compromise, and perhaps we could consider various options here to enhance future organization capability. One of them is a deployment of national technical means, and this is probably the things which Anders knows better than me. There was a very successful deployment of Swedish defense establishment mobile xenon detection station for the first DPRK explosion, and they succeeded with the detection of xenon. So this is one solution. Another solution is to, for the state parties to consider establishing the national cooperating facilities to expand this network. And as I said, it is possible in principle. It is not prohibited by the treaty to revisit the issue of design of verification system and enhance again the future organization capability. I could say that yesterday, yesterday probably, one of my colleagues who made a presentation, no, it was on Monday, on this issue of detection of radionuclides, after his presentation came to me and said that on his view, it would be better to suspend a collection of particulates and instead enable all the station to detect or to collect samples related to noble gases. I could add that the state from which this person came does not support SnT.
Yeah, I would agree with what my colleagues already said, and I would like to add that the interpretation and evaluation of the data, in this case it is quite complicated because of the confounding background, and even if we have some information from the stack, still it is a non-trivial task, and I think there is enough room for activities, contributions from the scientific community here. So from the point of view of inverse modeling, only like a small fraction of the scientific community engaged in this field has turned towards contributing to the verification of the CTBT. And as we are here in the SnT conference, I think, yeah, I would like to launch this appeal to my colleagues outside the CTBT community to consider this very interesting problem as something where we can do more in terms of like data assimilation and improving the source localization, source quantification, and so on, inverse modeling methods.
Okay. So should we then try, we have a couple of minutes left, a last question from the audience, if somebody is okay, please.
Yeah.
Two brief observations. One is that I have sort of thought, at least in my own mind, that to confine a conclusion that an underground explosion is nuclear solely to radionuclide information is perhaps too restricted, at least for large explosions. It seems to me above a certain point, the ability to concentrate chemical explosives in a single point becomes not very credible. The second point has to do with the crowdsourcing information and national technical means. The treaty is the first multilateral arms control treaty that I know of that explicitly provides for the use of national technical means in arriving at judgments of verification. So it's quite possible for a state to acquire crowdsourced information and make it part of its own approach to addressing questions of compliance with the treaty.
Pierce, I think you had the final word on our panel. Thank you so much. And I just wanted to thank Ivan Kitov, who is the mastermind behind the scenes helping us get organized. Thank you very much, Ivan. And thank all of you, thank our panelists, my co-moderator, and enjoy your lunch.